fantastic organization. A lot of work for you. You're probably taking a vacation afterwards.
Definitely.
Yeah.
You can change slides this way, and you can point on the screen with the top.
Oh, hang on. So this is the laser, is it?
Yes.
And this is a back and forth.
Yes,
Oh.
but when you go back, you have to click twice.
Oh, I have to click twice. Okay,
For
that's
some
very good to know.
reason.
Yeah,
Just seems
okay.
to be a PDF thing.
And I can't use this here, so I shouldn't touch this.
You can use this.
Up and down.
Like that.
And twice again.
Yes, and twice again.
Okay. And this one's right. Okay.
What time are we on? 9 a.m. Good morning, everyone. I'll give you 30 seconds for the
Morning, Lexi.
Morning, thank you. We're gonna make a start now. Sorry, is that's okay? Thank you. So we're gonna make a start this morning. I know probably people will still be filing in for the next half an hour. But this morning in our final session of the conference, we have one invited speaker, one keynote speaker. We have 3 contributed talks today rather than 4. So we'll have a couple of longer breaks today to do the poster sessions. And then we'll finish off the conference with our conference summary speaker, Joseph Silk. So I do just want to say, while I'm here and waffling, thank you to everyone for making this conference happen, to all the invited speakers, to all the presenters, the poster contributors, the organisers, the attendees, the LIS technical staff. So I never quite expected the conference would be such a good turnout, and it seems to have gone quite well, in my opinion. So thank you all for making that happen. So I'm going to start waffling and let Roya Mohai take the floor.
Thank you. Thank you, Alexia, for the invitation and for this organization. So I'm going to be telling you about cosmic dipole anomaly. And anomalies in general arise when there is discrepancy between what you measure or you observe and what a theory predicts. And this anomaly also arises in the same context. And it really arises in our quest for a standard frame of rest. And I will show you why that is. So if I ask you a simple question as what our velocity is, you might think that this is ill-defined. What do I mean by our velocity is a relative quantity. So suppose I take S. S is going around the sun at a speed of 30 kilometers per second. This has been known for centuries. But the sun itself is not at rest. It is going at a speed of about 200 kilometers per second around the center of Milky Way. Milky Way is a weird galaxy. All the galaxies are going apart, but Milky Way is heading towards Andromeda, so itself is not at rest. It's got a velocity of a few hundred kilometers per second towards M31. The barycenter of Milky Way Andromeda is also not at rest. It's going towards Virgo cluster at around 15 megaparsec from us. And this Virgo-centric infall has been known for more than 50 years. And as you've seen yesterday, I think, in the talk of Daniel Pomar, the whole of this thing is moving towards the great attractor, and the great attractor itself is not at rest. So there is this flow for as far as we can see in our local universe. Now the question is, can I find a standard frame of rest? How far do I have to go before I reach a frame that is not moving respect to a yet larger frame? And the answer is provided by CMB. So CMB, this is background CMB, and it's almost a perfect black body radiation, and you can attribute to this black body a single temperature. There are tiny fluctuations, which we call primordial CMB fluctuations. These are of order of 10 to the minus 5, but they are so tiny that here I am fitting this theoretical black body radiation, and on top of that is the data and they're completely superimposed. So it's a perfect black body radiation, and it's a single temperature of 3K. Now, before going from here, the CMB background at 3K to order of fluctuation, which we consider primordial, fundamental, at 10 to the minus 5 Kelvin, there is a step that we have deleted and we do not see very often. And that step is the CMB dipole. This is a fluctuation that we clean up so that we can see this tiny primordial fluctuation. Now, CMB dipole fluctuation is 100 times larger than the primordial fluctuations. That is why we don't attribute them to the same origin. So we say that these primordial fluctuations that we have talked about and we are talking about so much are primordial. They depend on the L universe fluctuations, quantum fluctuations, inflation, and so on, whereas the CMB dipole has kinematic origin. It's just due to our motion. It's quite plausible because they're really 2 orders of magnitude difference. So how does it happen? In fact, if you have got a black body radiation and an observer is moving in that black body radiation, it would see a temperature dipole. And this was calculated in 1968 by Peebles and Wilkinson. And you see here in this simple black body formula, so you see that the temperature that is in the observer's frame is a cosine, so it's a dipole. And if you can measure this temperature, anisotropy, the temperature dipole, you can measure the velocity of the observer. And this is how our velocity was inferred from temperature anisotropy, the dipole of CMB. But even before that, Denis Sharma, being a visionary, actually, a year before that, he wrote a paper with Stewart in Nature, and he actually predicted that from a very simple, very nice cosmography in the local universe, from the velocities with respect to Virgo, from our velocities internally, and so on. And you see that he's got a, sorry, I'm getting these buttons wrong. So this is about a year earlier, and this is really has nothing to do with black body radiation. It's just a pull of these structures near us, and it's got a pretty good number, very near what we infer from the CMB. Now, this is of course okay, and probably the CMB dipole has a kinematic origin, but it's an interpretation. And so in physics, we like to have other tests, right? So the question is there a standard frame of rest that I can use to infer our velocities or not? And the answer is yes, actually. So distant sources like quasars have been used for decades by military for targeting very precisely, as we know, and by astrometers, people like in Gaia, like in Hipparchus, they were using these quasars as rest frames so that they would measure the proper motion of the stars. So why don't we use quasars as a second way, a second measure of our velocity? There's a problem. The quasars are not black body. They are not thermalized like CMB. So I cannot attribute a single temperature to the quasar. So I cannot do the black body exercise and find my velocity. I have to do something else. How do I measure the observer's velocity in the rest frame of quasars? And the way to do it is actually goes back a few centuries. It's one of the oldest ways of measurements in astronomy. And it goes back to James Bradley, who was a civilian professor at Oxford. And so I'm going to tell you a little story. When Copernicus, about 500 years ago, proposed that we are not the center of the universe, which is something we keep forgetting. So Copernicus was saying we are not the center of the universe and Earth has a motion. Astronomers tried very hard to prove that, to verify that, or falsify that by measuring the Earth's velocity. They were looking for parallax. And some of very prominent astronomers either claimed that they had actually found the parallax, which was then ruled out. So Bradley, being a very meticulous astronomer, he actually set up a little telescope with his friend Molyneux in somewhere near Kew Garden in London. At that time, it was in the middle of nowhere. And they were looking at these fixed stars. And what he realized was that these fixed stars, they were just making a circle in the sky. But he was realizing that this movement did not depend on the position of the observer, on his position of the Earth. It depended on the velocity. And what more important he found was that the amount of displacement of the star position did not depend on the distance to the star, which is what you would expect in parallax. And this was not parallax, this was aberration. Aberration is an effect that is displacement of the position of stars due to the motion of the observer, not the position of the observer. And in fact, parallax was discovered 100 years later because it's 100 times actually smaller. So it took a long time to discover that. Now, aberration is great. So if an observer is in motion, and you see actually in Bradley's formula, so there is the velocity here. So if I can measure the movement, the angle in the position of the stars, I can find the velocity of the observer. He didn't use a special relativity at all. This is a completely classical formula, and it's exact for when the velocity of the observer is much smaller than c. So if the observer is moving, then there's an aberration effect. It's a completely geometric effect. It doesn't depend on any of the properties of the source. It doesn't depend on the distance of the sources. It's very powerful. So you will see more sources. It's like a beaming effect in the direction of the motion. In fact, this more sources is due to, in the special relativity, we understand it as the solid angle shrinking in the direction of the motion and enlarging in the back direction. There is an extra effect, of course, as you can imagine, you have already imagined, is that the frequency of the sources will change in the direction of the motion. So in the direction of the motion, the sources will be brighter because the frequency will increase, the energy will increase, and in the back direction, they will be fainter. This effect is known as Doppler boost. Now, how do I use that, formalize this all together to measure our velocity in the rest frame of quasars? This is due to Ellis and Baldwin about 40 years ago in that beautiful place in Crete. Alexi, I hope next conference you organize there. So they were attending conference and they wrote this fantastic paper. I wish I had written this paper. It's a very nice paper. So it's very simple, actually. So the idea is just a simple Lorentz transformation. So you do a Lorentz transformation, two observers, one is moving, another one at rest in the frame of sources. And of course, there is a boost of the frequency. There is change in the solid angle. This is the Lorentz factor, the delta. The fluxes would change, and I will tell you very shortly what alpha is. And the number count, as a consequence of that, will also change. So the number of the final story is that for when the velocity is much smaller than c, the number of observed sources has a dipole structure in it. You see the cosine here, and it depends on the velocity of the observer. So if you can measure this number, then I can measure our velocity. And measuring this number is just very simple. It's a simple number count, right? And what are these alpha? So this is the amplitude of the dipole that we measure by just doing a number count. And this alpha is basically the spectral index. Source is power law, pretty good valid for quasars and radio sources. And X is sometimes referred to as magnification bias. It's basically the number of sources above a certain flux threshold, which is S star here. So let's do that. Now, this is very powerful. Before going further, I want to just quote a phrase from this. So they are saying in that paper that they wrote in that nice Greek island, that the great power of this test is that the measurement can be made and the result must hold for any source counts, whether in a wide or a narrow solid angle, for flat or steep source spectra, etc., irrespective of selection effects or source evolution, irrespective of source evolution, as long as the forward and the backward measurements are done in the identical manner. So it's a very powerful test. And to that, I add that this test is independent of distance. You don't need to know redshift. You don't need to measure distances. And it's totally, fully model independent. I mean, you've seen many talks in which we try to establish lambda CDM or FLRW metric, but we have to use some assumption of homogeneity and isotropy. Here, you don't have any assumption. It's fully model independent, and it's fully independent of distance. However, there is a problem, and the problem is that these quasars that you're using as rest frame, they are discretized, so there is shot noise. And you see here the shot noise, of course, it's a Poisson noise. It goes as 1 over square root of n. So in order to overcome that, for a kinematic dipole, which is, we think is over the order of 10 to the minus 3, you need at least 1 million sources. Anything less than that, you are having problem with shot noise. We have not had such a data up to very recently. So this data has actually been really fabricated by our collaborators. Subir and I collaborate with Nathan Sechrest, who actually works for Naval Observatory. And this is a cat-wise data. It's data coming from WISE satellite. WISE satellite is actually scanning 700 million objects. Oh, I think I'm running out of battery. 700 million objects, sorry. 700 million, but out of these 700 million objects, only 1.5 million quasars we have managed to extract. It's observing in 4 bands in micrometer. So these are terahertz. And you see this distribution of these quasars, 1.5 million. We have made a big cut in galactic plane because of the confusion. And now we can do our number count as the formula, the formalism of Ellis and Baldwin. And so before doing that, I've shown you the redshift distribution. So most of these quasars are very high redshift, which is what we want, right? We don't want them nearby, because nearby there is just a local anisotropy, and it would be confusing with the large scale isotropy. And so this is actually the number count dipole. It's not yet number count, but the number count would look something like that. So you see a dipolar pattern here. You've got more sources, fewer sources here. And now so the question is, what is the significance of this result? It could be just a statistical fluke, you know. It doesn't have to have a big statistical significance. So what is the statistical significance of this result? In order to establish that, we have run 10 million simulations. So these are not n-body simulations. These are just Mach Sky. So you get just random distribution of 1.5 million points, as it is in cat-wise. You put the same footprint, the same mask, the same spectra, and so on. And then you put an observer. So you put an observer at the center, basically, moving towards the CMB dipole at 400 kilometers per second. And the null hypothesis is that if that is true, then I should observe the quasar dipole, if the quasar dipole is just a statistical fluke. And so this is it. So this is the null hypothesis, an observer moving with a velocity of 400 kilometers per second, as it is expected from CMB, can see a dipole as large as that observed in the quasar distribution, which is very large, and this is the direction that we observe. So the direction is actually very close, but it is not the dipole that is given by quasars. Actually, the quasar dipole for this null hypothesis, it's lying at about 5 sigma here. Basically, you see that here. So the null hypothesis is rejected, and this result, if you translate it to sigma, it's got a significance of about 5 sigma. Now, of course, this result has been, so this was what I've been showing is a frequentist approach, has been confirmed by completely different approach by people who are using Bayesian approach, and they find the same result, so they confirm our result at more or less similar significance. Now, what is it saying basically, if we take this result as correct, is saying that our velocity respect to the CMB rest frame is not the same as our velocity with respect to quasar rest frame. It's almost twice as large. So you might say, okay, why do I care about this? Okay, so our velocity with respect to CMB and the quasar is not the same. Well, it's important. It's important, as Ellis and Baldwin themselves said in their paper. So in their paper, they talked about radio sources, but it's not different from quasars, as I will show you. So they are saying that if the standard of rest determined by the MBR, at that time they would say MBR, they would not say CMB, they would say microwave background radiation, and the number counts were to be in serious disagreement, one would have to abandon either the idea that the radio sources are at cosmological distances. Now we don't abandon that. We know that these sources are at cosmological distances. At that time they didn't, there was a dispute. The interpretation of the cosmic microwave radiation as relic radiation from the Big Bang, I don't think we want to abandon that. Joe, we don't want to abandon that, do we? And the third is that the standard FRW at that time, they would completely omit Lemaitre, so FLRW, universe model. So you have to abandon one of these three. And now we know pretty well that A, you cannot abandon, B, you cannot abandon. And this is the one possibility that you have to abandon if this result is to hold. The comparison of these models, of these standard of rest, provide a powerful consistency test of our understanding of the universe. So where do we go from here? And the question is, why is it? The question is, you would ask, why is it that if the two frames do not agree, I have to abandon FLRW metric? And the answer is here, basically. So this is a very simple question answer. So the standard FLRW metric is based on the cosmological principle, as you saw in the Francesco's talk yesterday. It doesn't hold, but okay, let's say it is. Cosmological principle is saying that the universe is homogeneous and isotropic, and a model that we call lambda CDM is based on this assumption. And I can use the lambda CDM and predict what my velocity is, because I have the power spectrum, I have all the Tuileries, I have the model, I make a prediction. And this is the prediction of lambda CDM of the velocity of the observer. This is the local group with respect to larger and larger and larger frame. And these are relatively local, you see. So this is lambda CDM prediction, and lambda CDM prediction based on cosmological principle is that at the scale of about 100 megaparsec, 0.03 in Z, almost, the CMB, I should basically be in the CMB rest frame, because my velocity should have converged to the velocity inferred from the CMB dipole. This is really the theoretical curve. Now, this is very nearby, and what we are actually seeing is here with the quasars. So we are seeing that this is the lambda CDM prediction. So it's basically saying that the CMB dipole is recovered very soon. And this is the rest frame of the quasars that we have got from the cat-wise data. They have huge discrepancy. So this is an anomaly. The data doesn't agree with the theoretical prediction. So you would say, most of the people would say, I want to keep lambda CDM, it's fantastic. It's explaining a lot of observations. Your result is due to systematics. And we've been here for the last 6 years. And you know, systematic is like the dark matter, you know, you don't know what it is, it's a systematic. So, well, I mean, so let's say that. So there are systematics, of course, in cat-wise. So there is always the problem of galactic plane. We have got a huge cut on the galactic plane. And there is the fact that the scanning pattern of Weiss is associated with ecliptic latitudes. So this we have also taken care of. And these results, there are many other systematics, of course, no deny of that. But this result, our result, has been confirmed by other groups, by other methods, using completely different analysis. So still, this dark shadow comes again, and people say, this is systematic. Okay, let's say it's systematic. What is the best answer to this criticism that is a systematic? Well, I abandon cat-wise. I look at a completely different database. I use a completely different data set, has nothing to do with cat-wise, different sources, different instruments, and I see if I get the same result or not. And then you should be convinced that this is not just a systematic. So what did we do? We look at a completely different data set, put cat-wise aside, just because, like many of you, we also want to believe that this is systematic, because it's so simpler to deal with FLRW. Any other deviation from FLRW, like Bianchi, like Sekeres model, they're just so complicated. Who wants to work with those? And you can't write any papers because they're just so complicated. So it's much better to keep FLRW. But let us see whether it's a systematic. So let's look at radio data. So this radio data is MVSS, and this is older than CatVice, has no shared sky scanning pattern with CatVice. This has no shared instrument design because MVSS is a telescope on the ground. CatVice comes from VICE, is a telescope in space. They have no foreground systematics. One is on the ground, one is in space. And they have got basically no shared sources, completely different sources. And so this is a distribution of MVSS sources. We have got far fewer sources. It's about 600,000 radio galaxies in a completely different frequency range. Here it's in gigahertz. CatVice was in terahertz. So, and here are the two. You see, they have got different cuts. So MVSS, the peculiarity it has is that it doesn't see below the 40 latitude, 40 degree latitude. And this is what we are finding directly a dipole in the number count for the MVSS. And so you see that the direction of this dipole is very similar to the CMB direction, but the velocity of the observer inferred from this dipole is much larger. You see, it's more than twice that inferred from the CMB. And this is a statistical significance analysis of NVSS to the left. So you see these are the CMB dipole offsets on the y-axis. This is the dipole. This is 1, 2 sigma line, and this is the data, the number count from the radio that's coming. So it's above 2 sigma, it's almost 3 sigma. And this is from the CatVice. It's a very conservative analysis, and this is almost 5 sigma. Of course, this is a lower significance because you have got 500,000 sources. Here you've got 1.5 million sources. So what does it say? So I emphasize again, they have basically shared sources is 1.5%, which we remove actually when we analyze NVSS data. So we've removed those. And this is basically you have no shared. So they're completely orthogonal catalogs, and they're showing the same results. So actually later on, in 2023, people came and did a combined analysis of radio sources, and they found that the radio data alone confirms the anomalous dipole at about 5 sigma. This is a completely different group, different analysis, and mixing, well, not mixing, properly taking account of different radio data. So I suppose we cannot, after all of this, that different group, different data, different analysis are confirming the same results, say that it's systematic. So I can say something else. I can say actually that Ellison-Baldwin formula is wrong. So people evoked lots of things, source evolution, redshift, and so on. But OK, let's say Ellison-Baldwin formula is wrong. Let's take a completely different approach, totally different. I'm not using any spectral indices. I don't care about the magnification bias, completely different. I'm just going to use a very simple test that is very often done in cosmology, basically spherical harmonic analysis. You do a spherical harmonic analysis, not the Ellison-Baldwin test. You just say, OK, I'm looking at distribution of quasars. I want to know their clustering properties. I don't care whether it's due to kinematic or anything else. And this is what you get. So this is the CMB dipole prediction. And this is a dipole that is coming from just a clustering analysis, not an Ellison-Baldwin test. And you see they are discrepant. You see that all of these other higher multiples are more or less fitting. This is the lambda CDM prediction. But the dipole, look at that. This is the dipole from data, and this is what lambda CDM is predicting. So it's discrepant. And this method doesn't use Ellison-Baldwin. So it can't be Ellison-Baldwin. It can't be systematics. This data, this cosmic dipole anomaly persists across different data sets, different method of analysis, different formulations, different tests. So what is it? And where do we go from here? So you can live with this anomaly and say, well, I don't care. There is also Hubble tension, but I'm doing other things. These are just little things, and they will just evaporate away. So what's going to happen here? Let's look at history. So what happens to anomalies usually in physics? Should we take these anomalies seriously, or should we just put them aside and do whatever we are doing? Well, the very first, not very first, but the most, for me, because I worked on this, the most interesting for me anomaly was in the 19th century, advancement of the perihelion of Mercury. So Newtonian mechanics at the time was working fantastically well. It was fitting the orbits of the planet, the orbits of the satellites of the planet. It was predicting, making a lot of prediction. But there was a little tiny mismatch between the prediction from Newtonian gravity and the observation. And that was done by Leverrier, who was working not far from where I work in Paris. So Leverrier was looking at the orbit of the Mercury around the Sun. And he was saying that this perihelion of the orbit was advancing little tiny bit. So how tiny is the tiny bit? The number is really mind-blowing. It's 43 arc seconds, not in a year, 43 arc seconds in a century. So he was measuring. He didn't have AI. He didn't have any of the Python, mathematics, or nothing. He was measuring this advancement of the perihelion of Mercury. And he couldn't explain it. He did a lot of things. He even, in his calculation, took into account the effect of the planet's gravity on the Mercury. Every single one of them. And he couldn't explain this 43 arc second. So Leverrier actually originally found anomaly in the orbit of Uranus, and he predicted the existence of Neptune. So he used that. He said, okay, here I predict there's another planet. He called it intra-Mercury planets that we don't see, but it exists. And that is perturbing Mercury's orbit. And if you look at the maps that were created at that time, this planet actually appears. You see there is this Vulcan. There was this Vulcan planet that was proposed by Leverrier to explain the advancement of the perihelion of Mercury. And even astronomers were claiming that they actually find the Vulcan. Now we know that it doesn't exist. We know that we need Einstein general relativity to explain the advancement of the perihelion. So there was a paradigm shift because of that anomaly, because that anomaly was taken seriously by Einstein. Actually, Einstein made it his job to explain the advancement of perihelion. The first version of general relativity that he wrote down, he threw away because it couldn't explain the advancement of perihelion. Now, there is the second anomaly in physics that we all have heard of. And that is the ultraviolet catastrophe. More or less at the same time, in early 1900, people were trying to explain blackbody radiation. Rayleigh and Jean, they spent a lot of time, and they found a formula, Rayleigh and Jean, and this formula explained the blackbody radiation at very low frequencies. But it diverged when you went to higher frequencies. Then there came many other modifications of Rayleigh and Jean. So there were Wien's model who explained actually at the high end, but couldn't explain at the low end. This went on, and there were many tweaking of the Maxwell law and so on, until there was the Planck quantum mechanics, actually. So this formula that was put forward by Planck, the beginning of quantum mechanics, explained this blackbody radiation perfectly well. So there was this paradigm shift again because of the anomaly. Ultraviolet catastrophe led to quantum mechanics. But there are other type of anomalies that are still lingering in physics. And let us look at that. This is a famous anomaly in particle physics. The G is the gyromagnetic ratio of muons, and the magnetic moment of muon that you measure very precisely using quantum field theory does not really agree with the one that is observed, that is measured by Fermilab and so on. Sorry, sometimes not working. So that has been unresolved for about 20 years. In particle physics, there is a general consensus that we should work on this and try to resolve that. There is another anomaly that is remaining unresolved. So it's Webb anomaly. It's basically Webb has been measuring fine structure constant from the different sources in the universe, and is finding that this fine structure constant is not really constant. We don't know what it is. Maybe it's an anomaly, maybe it's not. Maybe it will lead to a paradigm shift like it did here. Maybe it will not. Maybe it will go away. And then there is the anomaly of all anomaly. I don't know whether you want to call the problem of lambda an anomaly. It's more than an anomaly. What we are measuring for lambda, let's say if we believe those measurements from the observations, is very different from the prediction of quantum field theory. This prediction is very precise. So it's like 10 to the power of 60 at least, order of magnitude difference. But maybe lambda problem is something bigger than anomaly, something that would lead to a fundamental change in our understanding of the universe. And then there is our cosmic dipole anomaly. Maybe it's related to the lambda anomaly, maybe related to the other anomalies, we don't know. I'm writing here, it's unresolved for about 5 years, because really it's with our CAT5 data that this anomaly was established at about 5 sigma. Before, people were talking about this with radio data from 2011, actually, but because the data was not, in some sense, you didn't have enough sources, the significance of those results were not really high. So I would say this is fully established since the CAT5 data, since 5 years ago. So what is the way forward? Well, we have got instruments coming. LSST, so for all the young people who are here and member of LSST, please join us. Subir has a working group there. So this is the coverage of LSST that is done by my colleague Philippe Gris and Reza Ansari. So you see that this is the coverage of LSST, 40%, and millions and millions and millions of sources. This is the first year data from Euclid. This is the dipole, so this is the map made by my colleague Kenganga. So you see this is the footprint of first year data from Euclid. It's not much, but this is going to get better. And here you see the overlap with Euclid and LSST. This is done by Reza Ansari. So you see these blue contours are the Euclid final data, basically in 5 years' time. The DR3 actually third release of Euclid, if I'm not wrong. And you see this is going to cover all of that. And these sort of faint gray shaded regions are the LSST. So most of the sky will be covered by the two, and they will have a fantastic overlap. And of course, an excellent one. So these data, basically, Euclid DR1 is going to be released in October. LSST is 2028. And Euclid, of course, you need more data to come, so that would take another 4 or 5 years. But there is a data that is already available, and that is from Spherix. It's a fantastic full sky, again in infrared band. And it's a full sky, and an additional advantage of Spherix is that it's got a measurement of redshifts. The measurements are not as precise as DESI, but good enough for this purpose, whereas with Euclid and LSST, we don't really have spectroscopy, so we have mostly photometric redshifts. And here I want to finish with a phrase from Jim Peebles. So Jim Peebles, who has written this essay in 2022, he says, well, the lambda CDM cosmology passes demanding tests that establish it as a good approximation to reality. The theory is incomplete. So I'm very glad one of the founders of this lambda CDM is saying that this theory is incomplete. Of course, and open issues are being examined in active research programs. The dipole anisotropy in the distribution of objects at distances comparable to the Hubble length is about in the direction expected from the kinematic effect if the dipole anisotropy in the CMB is due to our motion relative to the rest frame defined by the mean mass distribution. But the dipole amplitude is at least twice the prediction. This anomaly is about as well established as the Hubble tension. Yet the literature on the kinematic effect is much smaller than the 344 papers. This is in 2022. Now it's about 3,000 or 30,000 papers on Hubble tension. With the phrase Hubble tension, in the abstract, in the NAS astrophysics data system. I expect the difference is an inevitable consequence of the way we behave. So I leave you with that. Thank you.
Thank you so much for that incredible talk, and it was really, really well presented. I really loved that. Thank you. Questions from the audience? Yes.
Yeah, thanks. That was very beautiful. I agree. You know, the inference is that when we see the discrepancies we compare with the CMB and the various other catalogues, we may not have gone out far enough to get convergence. So do you think the new surveys that you mentioned will necessarily, they will certainly be deeper than the ones we have today, but will they go out far enough? It may be that the CMB is anchored so far away, there's a huge space in between redshift 0, redshift 1, and you know, the last scattering surface. So what is your feeling about what could be lying up?
Yeah, first of all, if that is true, then still, even those FLRW metric cannot accept that, right? In lambda CDM, you cannot have such a structures at distances of above 2, 3, the redshift of 2 or 3, right? This is not allowed because it's going to be homogeneous and isotopic, as I showed you. So even if the data proves that there is some sort of convergence, this is not at all expected that this convergence should arise at redshifts of about 3 in the standard model. So standard model is basically still on the question. And the second thing is that, so there are two things. There's the convergence to the CMB dipole because of the local pool of the local structures, which was, I think, very nicely presented by Daniel yesterday. And then there is this other test of going really far, basically to redshifts of about 1. And there you are not even looking for convergence. You're looking to see whether that rest frame agrees with the rest frame of the CMB. And that is what the standard model is saying. It's basically saying that the rest frame of galaxies in a radius of about 200 megaparsec should be the same as the rest frame of CMB, apart from little fluctuation. It's definitely not saying that the two should disagree at about 5 sigma. That's not in the standard model. And the future data showing there's convergence behind 4, still that would be in direct contradiction with the FLRW.
Yeah, the question is 200 megaparsecs enough? The next generation will get us, somewhat further. Will that be enough? It's a huge parameter space that
Yes.
we don't really know what could be lying out.
Yes, exactly. But that is, but we are not talking about a few hundred megaparsecs. We are talking about gigaparsecs. Quasars at redshift of bigger than 1. So this is what I was showing you here. So this part here is, I think, very nicely presented by Daniel yesterday, right? You're looking at local universe and the flow and so on. What we are looking at is here. So here, I mean, you go above z equal 1, galaxies, they're very rare. So I don't know what other sources you want to use. You're using more and more quasars and radio sources. So this is what we will see with the spherics. As with galaxies, we can actually look at lower redshifts. Of course, it would be very nice to fill up this gap, as you said. I mean, this gap here, this will be filled up. And we will understand what's happening. You see, a redshift tomography would be very nice. And that's definitely is going to be achieved with the data, coming data.
LSST is going to prove that whole range. So you
Yes.
right that cosmic flows 4, as we heard from Daniel,
Yes.
goes out to 350 or so megaparsecs.
Yes.
If it could be pushed a bit beyond that,
Yeah.
it would be quite interesting.
Exactly, yeah. So we'll see how this thing goes here. See? This is data, basically. So you've got Daniel's data. I've also got some data I've not shown you, but Daniel's data is much, much more up to date. Okay, so I've gone, yeah. So this is basically the data, right? These are all data, these data points. And you don't see converge, doesn't converge. But this is very nearby, right? And nearby, it was always a question. I mean, for half a century, it's a question, There is Lauer and Postman saying, okay, there is a bulk flow, and then, there are others coming, no, the gate attractor is where convergence is. First, they thought this Virgo is where the convergence is. Then it was great attractive. Then Shapley. And now you have to go beyond Shapley, you see. So that is why we decided, actually with Subir, we decided, okay, this is very, we have to wait. So let us look at really, really far, where the question of isotropy and homogeneity is really clear-cut. And that's why we looked at quasars and radio sources.
Any other questions yet?
So you were talking about the consequence of the Ellis and Baldwin test, and that led to the FRW model being wrong. Have you considered what about if the CMB is not the relic radiation?
Oh, yeah, but that you have to ask Joe. I don't think he would agree with that. No, I think now we have pretty good reason to believe that is relic radiation. So that was one of the things that Ellis and Baldwin, but I think that we don't have to discuss much because almost all of us who dispute on this cosmic dipole anomaly agree that CMB relic radiation is. So where is my Ellis and Baldwin thing?
Yes, I was more interested if there was any theories that might have explained the dipole thing, or not, if that had been considered.
Yeah, so most of the efforts now, theoretical side, is to basically look at different metrics. So, in fact, so I had something on that. I hope it's still there. So,
the CMB spectrum, because that is the real evidence.
yeah.
It is primordial.
So you see, you can have other metrics, right? So this is FLRW, and you see that it's homogeneous isotropic, this one. But the universe doesn't have to be homogeneous and isotropic. It can be homogeneous but not isotropic. So it can have an axis. It's the Bianchi models that people are actually considering to explain this dipole anomaly. There are quite a few papers, very nice papers. It can be inhomogeneous and isotropic. It's the Lemaitre-Tolman-Bondy models. Or it can be completely inhomogeneous as well. So these are Steker's model. But look at these metrics. These are just so complicated. I mean, in FLRW, you just have one scale parameter. In Bianchi's, you've got 3, and here also. And look at that Steker's. I mean, a lot of free parameters. So that's why most of the people are looking at FLRW. Yes, Marco.
A couple of comments.
Yes.
I don't have a problem with complicated metrics.
I know.
The Kerr metric is terribly complicated.
So excellent.
Nonetheless, I described the rotating black holes, and we don't have a problem with that.
But that's excellent, yeah. That's excellent, Marco. Let me answer that. So why don't you, if you don't have a problem with this, why don't you use them to explain cosmic dipole anomaly?
I agree. I mean,
Good work for you to do. We need help from you.
Isotropic model, I just want to make a comment that related to the previous question, that there have been tests of an isotropic model in the CMB, Daniela Sade, Irania Perez.
Yeah, sure.
And the constraints are very strong.
Yeah. But there's still a few remain, right? I don't know, Bianchi 9 or something?
The only one that didn't constrain is Bianchi 9.
Yeah.
But
So.
they said, I asked them about Bianchi 9, they said that the constraint on that instead would be very weak.
So there's still possibilities in Bianchi's.
I wanted to ask you a question. I don't know how many quasars you have at very high redshift, but if you try to use, say, just quasars at Z greater than 3, say, would you have enough quasars to make
Not really.
for the moment?
For the moment,
I
not.
mean, the question is, if you use only high redshift quasars, do you get the same answer?
This is very high redshift. This is bigger than 1. And you know, bigger than 1 and bigger than 3, it's distance-wise and time-wise is not very different. So this is the redshift distribution. And you see that, you see? 3, when you go to 3, for cat files.
For the moment, yes.
Yeah, but with future data, yes, I hope so. I hope we'll have more. Yes.
If you use just those bigger than 2.
Yeah, you can, but then you have got a significance of less than 1. Because you see, there's a shut noise, right? It's the square root of n.
Yes,
Right?
so it's still
Yeah.
a problem.
Yes,
So
yes,
with next
yes.
surface you can
Yeah,
do that.
so that goes back to Joe's comments that you go to higher and higher with these new data, and that's why these new data are important, and that's why we need young people who are here are members of LSST and Euclid to join us, because we have got working groups in both of these.
Is it great talk?
Thank you.
Very interesting. So, have people thought about using 21 centimeter intensity mapping because it's in a way similar to CMB, that you can analyze the dipole?
So they're using LOFAR, right? I mean, Dominic Schwartz, I think, doing a lot of LOFAR predictions, but I'm not sure if they have got.
Like future.
Yeah,
SKA.
and SKA, yeah, of course. SKA would be one of the things I haven't mentioned, but because SKA is just very far, right? It's 2030, beyond 2030, but absolutely it would be excellent. It would be like MVSS, but with millions and millions of sources. That would be fantastic.
One of the results you showed included RECS, which is a pathfinder.
Yeah, that's right, yeah. So RAC is a pathfinder for, yes, RAC is a pathfinder, oh, sorry, it's after that. It's a pathfinder for SKA, but absolutely SKA is, yeah, that's right. Yeah, I think it's here. Yeah, this one. So you see here, this is RAC, the red contours, and this is really pathfinder for SKA. And yes, yeah, SKA would be perfect, but it's in like 10 years. It's a bit too late for me, but for young people, yeah.
So, if you divide your samples into different redshift beams, do they all give the same anomaly direction, or they are different?
So this is something, as I said, tomography we would have to do. So we can't really do this because it is not. This is not enough. But we have done it almost, because so in a work that I did with Subir, two of our other colleagues, we used all-wise, which is at lower redshift. We find a still anomalous dipole. It's not at much lower redshift. It's at about it's a median redshift of 0.14. So we found the same thing. And when you go very low redshift, then you've got what Daniel is doing. So it's basically local universe cosmography. And with Euclid, with LSST, with spherics, we'll have the redshift, so we can actually do this redshift tomography. So this is really something very interesting to fill up the gap, actually, to fill up this gap here, to understand. And this is what we mean by understanding the universe, right? We don't know what's happening here. What is happening here? And this is what the redshift tomography will do.
Thanks. This might be somewhat related to the previous questions asked as well, but I'm not too familiar with any cosmology metrics that, other than the FNW metric. Are there any that incorporate kind of kinematic motion in the metric itself? So, for example, like rotation, if you have just a general motion of all objects in the universe relative to the CMB, then you would get a dipole. Are there any metrics that incorporate that?
Marco, it's a question for you. He doesn't know. So, well, I suppose these people who are looking at, so there was a recent paper looking at some Bianchis. So part of that could come from the metric, of course. That's why, changing the metric would change. And these metrics actually allow for universe to be anisotropic, right? So
there is a general problem that any vorticity, rotation, etc.
would decay.
Has to decay very rapidly with redshift.
Yeah.
So if it is important today, it would have been far more important in the past. And that would destroy our current understanding of the early universe, nucleosynthesis, etc., etc. You can't, all the data is consistent with the universe being FLRW radiation dominated at that time. So my personal opinion is that what we are seeing is likely to have arisen much more recently, perhaps associated with structure formation, which is around redshift of 1 to few, rather than being primordial, because then it's kind of hard to understand why the model of the early universe is so successful.
Yeah, exactly. Yeah. No. I mean, CMBs.
With the late universe, and the most significant thing that happened in the late universe was precisely the departure from homogeneity that we call structure formation.
Yeah. And that is very.
How it happened, I have no idea. And I'm sure that any simple calculation on makes shows a negligible effect. But this is something we are seeing on the sky. So.
Yeah. And it's funny that, lambda is also a rise. I mean,
well,
lambda is also a structure formation, right?
Exactly.
Yeah, so something about the structure formation we don't understand.
There's something about the redshift of order 1 that
Yeah.
something happened in the universe, and that's what we interpret either as dark energy or now we are saying is dipole anomaly. So I think it's something, yeah.
Some great questions. Are there any final questions before we have a long break? If not, then we can continue discussions out there, and let's thank our speaker
Thank you.
one more time.
Thank you. Good to see you. Oh, yes, sorry.
point correlation learning is not a good way to look for that kind of periodicity. But I think, I guess, last one is these cases matter.
Can I just flick through the slides quickly?
One second.
Ah, sorry.
Sorry. It's because
Yes, but
for some reason.
It's not working? Yeah, 22nd April. That's good. Just quickly flick through.
And then you can move it.
Yeah.
Brilliant. Sorry about all that.
No worries.
It's because when it says, enable editing, it's like a protection thing, so you have to get rid of it before you can broadcast it. Anyways. All right, welcome back everyone. We now have a series of 3 contributed talks. Our first speaker is Sankalan Bhattacharya.
Great, thanks. Well, hello everyone. My name is Sankalan. I'm a second year now PhD student at the University of Edinburgh. So I'll be presenting some work I've been doing with Professor Avery Mikeson on modeling fluctuations in the ultraviolet background, or the cosmic photoionizing background. So I've structured the talk as follows. First, I'm going to motivate why we want to model the ultraviolet background, why it's interesting, where it sits in large-scale structure analysis. Then I'm going to set out the transport physics, or the radiative transfer modeling that we're doing and how that works and what the important features are. Then I'll be talking about the source statistics of the ionizing sources and how all of this imprints signals on the ultraviolet background and on large-scale structure observables with some illustrative calculations. Okay, so we're in the era of precision cosmology, where there are many large-scale structure surveys, including, for example, DESI, which has inferred the BAO position using the spectra of hundreds of thousands of spectra of quasars at a redshift of 2.3. And we've already had a nice talk about the Lyman alpha forest yesterday, but I'll just do a quick recap of what the Lyman alpha forest is. So this observable is when you basically look at a bright backlight, like a quasar or a very bright galaxy. The light from the source streams towards the observer, and along the line of sight, it's intercepted by intervening baryonic matter. And these are these are neutral hydrogen reservoirs populating cosmic filaments in the cosmic web. And so the ionization states of these filaments will affect its ability to absorb light from this tracer. So if you look at the spectra, it'll be filled with a comb of Lyman alpha absorption features from Lyman alpha absorption of the hydrogen of the gas when the light streams towards us. And then you aggregate the flux, correlate it across the sky, and you have a tracer that is correlated with the matter over density in the universe. And you can use this, as I've printed a plot from the 2024 data release 2 from DESI, to infer the position of the BAO peak from the autocorrelation of the Lyman alpha flux power spectrum. So we want to model the ultraviolet background because this is the light that's able to ionize these cosmic filaments. So this bath of radiation that's produced in the late universe by quasars and young star-forming galaxies is usually assumed to be uniform. But we are going to argue that because the mean free path of the photons is very large, it's of the order of 350 co-moving megaparsecs at low redshifts, around 2.4. So we expect it to preserve a lot of the interesting structure and clustering of the sources of the ionizing light of the galaxies and quasars. And so any fluctuations are going to contain interesting astrophysical signatures that will canvass the IGM and imprint on large-scale structure observables. And so that's why we want to model the ultraviolet background. And how do we do it? So in the literature, there already exists many radiative transfer models, but which have extended the uniform background assumption by treating the system in steady state or with dynamics, but in an isotropic setup. So we want to generalize this so that we can facilitate the interesting source correlation structure of the system. So we want it to be an anisotropic Boltzmann hierarchy. We want to include memory effects from the population of sources, because these galaxies and quasars aren't expected to have been born an infinite time in the past and live to eternity. They have some compact emission history, and so they're going to imprint some memory into the radiation field. And we want to do this because we want to explicitly connect the ionizing source population statistics to the large-scale structure observable, and this may be a potential systematic to correct for future surveys which will aim to work at the sub-% level precision. So, what's the strategy? You just write down a transport equation to do your radiative transfer, and then we linearize this because we're working in the post-reionization universe where it is uniform up to small linear perturbations at low redshift. And this will give us some equations of motion, which will give us the radiative transfer linear kernels, which we can apply to source correlations. And I've just printed the formulation we use. So this is Lindquist's formulation of relativistic kinetics, originally used for neutrino transport in stars. And what are the features of the ultraviolet light that distinguishes it from other cosmic species normally modeled? Well, people normally model the CMB, or neutrinos, are called dark matter. And for example, the CMB photons have a thermal phase-based profile, like we know their black body. And also, they're a primordial relic. They're produced in the early universe at some almost isotropic boundary condition, the surface of lost scattering, and they stream towards us. But ultraviolet light is produced very recently. It's a highly collisional non-thermal system. It's produced by quasars and galaxies, which themselves form in matter over densities due to hierarchical structure formation. And we're looking at the driven linear response from this source emission and fluctuations in the emission to induce clustering in the radiation field. It's also feedback sensitive. The IgM absorbs this light, but its ability to absorb the light is modulated by how much radiation there is already there to ionize it. So we want a framework which can discern angular structure, memory, and the Poisson correlations. So this is, I'll detail it later, but the sources are discrete, but the radiation field is continuous. So you're smoothing over the radiation field, but the sources, such as the quasars, are rare discrete objects, so they have some shot noise. And this, when you apply the radiative transfer kernel, induces some clumpiness in the radiation field. So what are the basic dynamics? So we can start off with a simple dynamical description of fluctuations around the mean density of the radiation bath. And well, you get the fact that the universe is expanding, so the wavelengths are getting redshifted, so the photons that would usually be able to ionize the hydrogen are going to leave that band, some of them. You get a normal streaming kernel. This is the isotropic one. You get the fact that it's driven by impulses in source fluctuations, the negative feedback from the fact that as the IgM gets ionized, it's less able to absorb. And also it's coupled to the background evolution of the mean density of the fluid. Okay, and now we generalize this to an anisotropic hierarchy because we want to treat the full angular structure of the fluctuations. So you get your normal streaming cascade as you would with the neutrinos or the CMB photons. So a fluctuation in the monopole, so the density contrast to the radiation will propagate into a net flux in the radiation, and then anisotropic stress, so radiative stress and so forth. And it will produce higher angular moments, so finer angular structure in the radiation field. And this is important because, for example, the CMB, it's like an almost isotropic last surface boundary condition. But here, when the radiation is produced in the late universe, there's already inherent angular structure because these quasars are oriented and they're in matter over densities and they're beamed. They're not like light bulbs. So this kernel is important to properly treat that angular structure. We also bookkeep the gravitational effects because people are now wanting to do relativistic Lyman alpha forest analysis, and we need to check how important GR effects are on those scales. And people have proposed that spectral contrast may boost these GR effects, which are usually ignored in this analysis. So you get sort of CMB analogous, Sachs-Wolf, integrated Sachs-Wolf type effects. So there's local gravitational redshifting. The photons are basically losing energy on the ensemble of geodesics. It's a bit different from like the line of sight integrals you would do on the CMB. The sources have some velocity dispersion, so that's going to imprint on the radiation. And on the collisional side, this prescription is basically the dynamics on some gauged coordinate frame. And when you want to glue together emission and absorption physics prescribed on local flat proper times, you have to make some linear corrections. So I've just called them collisional Jacobians. Ultimately, we find that still all of these effects are sub% level contributions to the power at BAO scales, and it's only on much larger scales that they become important. And so large-scale structure surveys won't have access to them because the uncertainty in the biases will currently subsume these. Okay, so we have equations of motion for the radiation field. So we have a radiative transfer kernel to apply to source correlations. So what's so interesting about the source correlation structure of this system? So we have quasars and galaxies producing this light. Quasars and galaxies both follow hierarchical structure formation, so they form in overdensities and halos and galaxies. And so you'd expect the power from the source emission to have a contribution which traces the matter power spectrum. And you also get the fact that the shot noise of the sources will induce clumpiness in the radiation field. So the fact that these are discrete and rare, and at higher redshift they become even rarer, so the variance of these fluctuations becomes even more important. It becomes a more significant effect, and even dominates. Okay, now lifetime.
And the source is oriented randomly.
Yeah.
So so that picture is only of the ones that we are seeing, which are pointing towards us.
This isn't for the ones we are seeing.
What is the meaning of this term oriented? Oriented with respect to what?
I just mean that compared to a spherical light bulb, if you then have some beaming, right, you then have to prescribe whether it's uniform orientation, whether there's intrinsic alignment, there's just an extra degree of freedom you have the choice to introduce. So in the fiducial calculations I will show, we assume random distribution of orientations because we have no motivation.
So that's exactly.
But yeah. Okay, so source lifetime. So these quasars may have some active duty cycle, they're born and they die, so there's some characteristic emission history period. And this introduces a rich correlation structure in the radiation field, or in the source emissivity power. So the intuition I want to convey with this schematic is that if you imagine any spatial foliation, and if you want to look at two-point statistics, so correlations at some given scale, the Poisson clumpiness, the shot noise, when applied with a radiative transfer kernel, will be sensitive to this emission history lifetime, this parameter. Why is this? Because like if you imagine the radiation field here and here, in order to coherently correlate the shot noise, it will have to be engulfed by the active light front of the fraction of population of sources that are able to emit light within their lifetime to then be received at some cosmic epoch at both points. Right? So there'll be some coherence timescale. Another intuition I can give is maybe on for large scale modes, so low K, the photon crossing time is quite big. So it might be much bigger than the lifetime of the sources. And so the mode is able to independently sample many independent realizations of the source population. And so this is going to boost the effective correlation strength of the co-moving number density and subdue the coherence of the Poisson correlations. And this is like a memory effect. So this is propagated with non-Markov dynamics. And the other thing is the beaming. Okay, so if you have a bunch of spherical light bulbs, then you can imagine the radiation field is quite smooth. But if you suddenly imagine a bunch of torches, then you would expect a lot of angular structure, right? There'll be some turbulence. Okay, that was a bad use of turbulence, but there'll be some finer moments in the radiation field. And so power will be skewed away from the density contrast. And also just any point of the radiation field when feeling Poisson correlations will only be able to infer the fraction of the population of sources that are oriented such that they can point at that source at that point. And this will depend on the solid angle of the source that's producing the light. So there's a renormalization of the shot noise, and there's some skewing across the angular structure. So we can write down fiducial source population statistics analytically In order to do more precise and discern actual population statistics, this might be something you have to stipulate or produce numerically with some simulation, but I can show the sort of characteristic effects with a few parameters. So as I said, if you introduce like a lifetime for the sources, those are some parameters depending on the number of populations. If you introduce a beaming of the sources, that's another parameter. And they basically push power away from the monopole, renormalize its strength, and bind the coherence of the Poisson correlations with some time scale. Okay, so we have the radiative transfer kernel. We have the source correlation or minimal toy model for source correlations. Let's apply it and see what happens. So what do we do with all this machinery? Well, the point is that the Lyman alpha flux power spectrum, the clustering patterns depend on the clustering patterns in the ionizing background, right? So in linear theory, the flux depends on gas density, temperature, velocity, and ionization. But we assume that density, velocity, and temperature are well correlated to density, and so just trace the linear matter, and then you get some additional pieces based on the ionizing background. And so that's the machinery we've developed to compute. And if we plug that in, what happens to the observable? So on the left panel, I've described the full Lyman alpha flux power spectrum, the poles of it. And so I've shown the monopole, which distinguishes the shot noise effect most. So I can create a pseudo steady state isotropic system by just setting my beaming parameter to pi over 2 and making the lifetimes really long, like a gig a year. So everything is very coherent. And you see lots of power being added to very large scales. But if you increase the beaming, the correlation coherence breaks, and when you propagate that through, the power decreases on large scales. And if you decrease the time, the lifetimes, the same thing happens. And in fact, this bottom purple line is very similar to not even treating the radiation field dynamically, but doing a steady state description without any Poisson clustering. So this is a massive effect, and it's heavily modulated by the character of the astrophysical sources of this species. And if you put that through to the correlation function, you get very small, but less than % level pushing around of the BAO peak in position, and order unity modulation of its amplitude. And so overall, we have a signal that is in large-scale structure surveys. Even if they don't see it, that means that we can already put constraints on the astrophysics of the sources. And at higher redshift, when we expect the signal to be even stronger, it can be a potential theoretical systematic which may impede like dark energy constraints. So these are my conclusions. So this modeling framework has some ingredients, so it relies on various bias coefficients, and they obviously have associated uncertainty. And at the moment, some of these effects, like the GR effects, are just absorbed by those uncertainties. Also, it's quite an intensive framework because you're treating the angular structure of the field in hierarchy, same as Campbell class, but you're also, on top of that, treating a non-Markov system because you're including explicitly memory effects. But I hope that I've sort of demonstrated that ionizing source statistics imprint distinct large-scale signatures in the ultraviolet background. These present a currently underutilized or unused signature to do maybe galaxy evolution or AGN astrophysics using a cosmological observable. And it may be something that people need to think about if they want to go to higher redshift and work at even higher precision to do cosmological parameter inference. Thank you.
Okay, thanks for your talk. Any questions in the audience? Any questions? Could you just go back a slide? Yeah, here. So, could you just explain this this middle?
Yes. I mean, this is just to say that
I didn't quite catch what you were trying to say about this one.
the middle one is just to distinguish that this signal mainly shows up in the monopore, right? Because it shows up in the shot noise modulation shows up in the ionizing autocorrelation, but not in the cross correlations. And so it's not going to show up in the quadrupole of the power spectrum.
Right. Okay. Thank you. Sorry, any other questions in the audience? Everyone's feeling a bit shy now. Oh, yes.
Yeah. Hi.
Hi, thank you for the nice talk. I'm interested in the expansion that you did, where you say I have like the velocity, the temperature, and the density index, and I have the fluctuations from gamma. Is this for redshifts? No, it's not this one. I think it was earlier. I don't remember the numbers. Sorry.
Okay, sorry. Well,
But it's basically, when you're separating like the fluctuations from velocity, temperature, density.
oh, in the Lyman alpha.
And then with gamma.
Here.
Yeah.
Yeah.
Is this valid? Okay, no. So, does that separation apply at all redshifts? Like, after reionization, how much is that second component? Is that really relevant?
After, well, deep post-reionization, so this is at a redshift of 2.3, it's clearly a big effect. And the variance will be high at high redshift, but the prescription of treating the radiation field as smooth and doing fluctuations on top of it obviously breaks down then when you go very close to reionization. So the prescription might fail just because you can't do this linear perturbation theory. But the effect is there. Okay. Is that okay?
Yeah.
Thanks.
Any other questions? Or? Yeah. Okay. So thank you for your talk again. Let's just we will move on to our next speaker, Robert Shelton. I'll get you set up on there. Thank you.
Am I audible to everybody in the room and also, I suppose, online? Yeah, this is my presentation.
So you have a pointer at the top, and you can move side to side with that, I believe.
There you go.
Oh, you have to press twice if you're going backwards.
Oh.
For some reason.
Okay.
Thank you very much.
Interesting. So good morning, everyone. My name is Robert. I'm a final year PhD student at the University of Groningen in the northern Netherlands. Very nice city. And as you can see from my second affiliation, besides at the Astronomy Institute, I'm also at the Mathematics Institute over there. So this is a bit more of a theoretical talk that I'm going to be presenting today. Some research I'm doing with my PhD supervisors at the University of Groningen. All right, so maybe I'm preaching to the choir here, but let me start with looking at the cosmological principle. It's already been mentioned a couple of times in the course of this conference. Namely, at the largest scales, the universe should be homogeneous and isotropic, although maybe not anymore after the conclusions presented here. But nevertheless, in cosmological tradition, you assume these two things, and then almost immediately the FLRW cosmology is going to follow from these essentially assumptions. And with that, our favorite version of the lambda CDM model, standard cosmology, is going to follow. So all is good, except it's not. Recently, in particular with regards to isotropy, what I'm interested in, there's been some observed tensions, most of which have also we've come across during this conference. For instance, the distribution of supernovae that Roya was talking about this morning, Hubble parameter angular dependence, and some bulk flows that Daniel presented yesterday. And so these are, well, some hints that maybe there is something wrong, particularly with the isotropy assumption from the cosmological principle. And you could say, okay, well, also due to the effects that were mentioned this morning, maybe you could have like maybe one sort of specified direction in the universe. But then looking at this very nice picture from a recent review by Alluri et al. In 2023, they sort of collected many of these sort of direction-dependent effects or effects that yield some sort of directional preference. And you see that there's a lot of preferred directions that are not all in the same direction. So looking at this, and you still want to sort of prefer an isotropic cosmology, I mean, you can. Everybody's entitled to their opinion. But I think still there should be a reason or an opening to look at fundamentally anisotropic cosmology. So we leave out the isotropy assumption from the cosmological principle, but while maintaining homogeneity. And then let's see where that leads us, specifically within a mathematical context, or the mathematical swing to it. All right, so being mathematical, the sort of definition that I want to use for homogeneity and isotropy are not the ones that I presented 2 slides ago, but really based on infinitesimal geometry. So particularly by introducing Killing vector fields, or infinitesimal isometries, they're also known. Killing vector fields such that this lovely partial differential equation should hold. But the important part is that these generate isometries. So that means that if you flow along one of these Killing vector fields, the metric where you started is going to match exactly the metric where you're ending up. And this is going to mean that anything that has to do with sort of anything that's derived from the metric, such as Einstein's field equations, is going to remain the same at your final location. So indistinguishable from a general relativistic point of view. Then homogeneity for me means that there's 3 spatial nowhere vanishing and independent Killing vector fields. And isotropy, that there are, again, 3 spatial independent Killing vector fields that vanish simultaneously at some point. Because suppose you're standing at that point, everybody around you is going to move according to their Killing vector field, but you stay put. Then effectively that means that people have been rotating around you. And this is why isotropy is often related with direction independence, because you can move directions around at will with these Killing vector fields. So, but I'm going to be not assuming that that's the case. So I'm only going to be assuming that I have 3 spatial nowhere vanishing independent Killing vector fields, but not that I have the ones from isotropy. All right. So obviously FLRW, or deriving FLRW as an immediate consequence, is out of reach. But I claim that still these homogeneous anisotropic universes are still nice enough to be studied basically analytically. And indeed so nice that people have already been noticing this since the 60s and 70s under the guise of Bianchi models. People have been looking into this. And why are these still very nice to be studying? Well, that's because you can show that the metric can always be written in the following form, namely that the metric components are going to be dependent only on your favorite choice of cosmic time, but then written on top of a frame that is not necessarily coordinate. So these are not necessarily dx, dy, dz, but some sort of more general choice of frame that can also vary from point to point in space. But what's important, because of the homogeneity assumption, you can show that this co-frame is going to satisfy this, well, slightly more complicated differential geometric equation, or here in the faded part, sort of a commutator relation between different vector fields. In a coordinate setting, this commutator would vanish identically, which is partial differentiation commuting. But for us, we do not assume that. But so the takeaway message is that the information about space is all contained in this point-dependent choice of this co-frame. Okay, so you go to this, now you try to write all of your differential geometry in this frame, and you find that for the Levi-Civita connection, the Christoffel symbols are going to be slightly altered in this way, namely by adding the red terms, which are dependent on these structure constants C. And because you alter the Levi-Civita connection, you also alter the Riemann tensor, the Ricci tensor, and the Einstein tensor. So you get a whole cascade of effects you'll need to be taken into account. All right, but since we can still sort of use this differential geometric structure, we can still attempt to do a lot of the same analysis that people have been doing for FLRW universes. Namely, we can find scalar perturbations of Einstein's field equations, where here I remind you the indices are in this non-coordinate frame. Then we can make maybe some assumptions, try to solve these. We superimpose these solutions in space-time with some sort of random amplitudes. Then we can compute a surface of last scattering. And then we restrict the solutions of 0.3. We restrict them to, well, the SLS of 0.4. And then we retract to the observer. And by following these steps, what we effectively produce is a CMB map that we sort of produce at the time that the CMB was produced. Then we retract that to us, and then we see what that's going to look like in such a generally anisotropic universe. All right, so this is a very general step plan that you may or may not be able to do with pen and paper. But for illustration purposes and to be able to definitely say something, I want to be using a particular example. So the example is I use a Bianchi 5 model with a general, well, with this form of the metric. It might be a little bit of an oversimplification to use this metric, but in Q&A maybe we can discuss it a little bit further. And I use my fluid flow is just along the temporal direction. But importantly, I have these structure constants that are non-zero. And that's going to alter the Levi-Civita connection, as I mentioned earlier. But in order to make this into something that we can compute with, and also put into an actual computer to produce some images for us, we are going to have to choose a coordinatization. But this choice of coordinatization, I want to emphasize that this should be separate from the choice of Bianchi model that we've made. Namely, to a Bianchi model, there can be associated many specific choices of coordinatization that could fall into one certain Bianchi model. So this is just one choice of coordinatization that I am going to be using. Okay, and then I'm going to perturb Einstein's field equations. This is step one. So I'm going to use a simple perturbation in the Newtonian gauge, just a scalar perturbation. And yeah, for the Einstein tensor, or the perturbation, how you do it is as per usual, but there are some more extra terms, and you don't have terms falling away or terms simplifying nicely as you would have in the FLRW case. And for the energy momentum tensor, you need to generally assume that it's going to be of this imperfect fluid form in order to capture the anisotropies that may be arising from your choice of Bianchi model or choice of anisotropic cosmology. If you set these equal to 0, then that's an additional assumption that you're making on your cosmology, which at this stage I'm not willing to do yet. So in general, you also need to perturb Q, this is the momentum density vector, and pi, which is an anisotropic stress tensor. All right, so for my assumptions, in order to create something workable, I'm going to use adiabaticity. So I'm going to assume that the pressure perturbation is going to be proportional to the density perturbation. That I don't have any scalar anisotropic stress, so that boils down to setting phi is equal to psi for my Newtonian perturbation, and then going to assume an equation of state. And then once you do the calculations, we turn out to be very lucky, namely that this Q vector is identically 0, that the fluid flow U that I introduced is geodesic, so that also simplifies some terms, and that also shear and vorticity are vanishing, so we also don't need to take them into account. But the perturbation equation that's going to govern phi, or psi in my case, is going to become this one. And you see here in red, in particular, there's a term, and that's going to look a little bit like a Laplacian term. And in fact, that is a Laplacian term. In a more general version of these equations, you do see indeed as a Laplacian. But from our case, since we know the metric, we could write it out fully. All right, so if you look at this equation, all of the other terms, so the Hubble parameter, the scale parameter, etc., they are only dependent on time, on cosmic time. So this equation actually turns out to be separable into a Helmholtz problem, essentially, an eigenvalue problem for the Laplacian, and then just a temporal ODE. Temporal ODE, we just plonk it into a computer and it can solve it. But for the spatial equation, it's a little bit more interesting. We can try and solve that for its eigenvalues and see if that's possible and what comes out. And it turns out that the solutions are plane waves in the YZ plane, and then times some sort of funky Bessel function. So it's going to be plane waves times a Bessel function with these meanings of the several parameters that we've needed to introduce in this process. And this is just an illustration of what this Bessel function is going to look like. So it's going to emphasize, well, depending on the parameter choice, it's going to emphasize one particular X region more heavily than other X regions. All right, and then to find the source of last scattering, basically that's going to be a null geodesic ball that's going to center at your redshift of choice for the CMB. And so the way you want to do that is basically you start at the observation event, and then you extend null geodesics in certain directions, and you extend them in, well, until you have reached the redshift of the CMB that you want to find. And then you find, well, your null geodesic ball. For our model, we see here that we have a YZ rotational symmetry, so also trying to calculate what this null geodesic ball is going to look like. It should also have a YZ symmetry, but not necessarily in the X direction. Something can happen, and indeed something does happen. So here in these directions, you see this is the YZ plane, and here you see the X direction. And well, I don't need to tell you necessarily that's very skewed. There's a certain preferential direction, and we'll see in a moment how that's going to manifest itself into pictures of the geodesy of the CMB that we're making. And this is also forgetting the time component, but I can come back to that in Q&A why I can do that. All right, and then, as I mentioned, the early universe is a superposition of waves. So computationally, we just need to decide which wave modes we are going to display. And, well, we make a specific choice on that based on compactifying YZ space. And also which amplitude to give them. We choose to give Gaussian random variables. All right, this is, I think, in the interest of time, I need to skip. But this is one single eigenmode that you see. And here's a sketch of why that is. I hope you could read that. And but in a Bianchi 5 universe that we simulated, this is a picture of a CMB that we're going to get. And the most striking feature here is that I want you to pay attention to is that you see here on the lower hemisphere that the structure seems to be very smeared out. Whereas here in the upper hemisphere, up to a certain point, the structure seems to be a bit more compactified. Now, why is that the case? So it's because for the upper hemisphere, essentially because the null geodesic ball is sort of expanding, you're seeing more of the structure in your field of view. Or in the negative x direction, in this way, you see that the null geodesic ball is sort of zooming in to one specific event or one very small collection of events. So that's why you see that the sort of washing out of structure on our on the CMB picture that we produced.
How did you define Z in your metric?
You mean the coordinate?
One scale factor.
Yeah, there's a single scale factor indeed. And
the angular dependence comes from what?
So the angular dependence comes from there, well, in this metric it happens that there is a allowed sort of transformation between y and z. So I could also replace y with a superposition of y, z as a rotation, and that shouldn't affect the metric in any way. So that's why you have a rotational symmetry.
But you just have the one scale factor.
That's right.
And you're assuming that recombination, all the physics that gives you last scattering is the same in every direction.
That's right, yeah. Or at least until the time of recombination, I'm assuming that's the case. But maybe we can talk about it also a bit further. All right, and here's the parameter choices that we use, but it's not necessarily necessary to go much into that. All right, so this is one of the things that we can produce, and then our next step would be to be looking for signatures in the power spectrum of such CMBs. We have been making steps into trying to calculate these, but the initial results that we found were very complex and very unexpected. So we are really doubling down on trying for a theoretical explanation, a more theoretical approach to finding out what these power spectra could be or what kind of features they could have. And then we also have some more suggestions and ideas for further research. One part in particular I want to highlight is studying large-scale structure. There is a paper out today by yours truly and my collaborators on the archive that also details how you can calculate density contrasts in such anisotropic universes, and it tells you exactly what sort of compensation terms you need to take into account because of the fact that you're living in an anisotropic universe. So this is also, we find, a good first step into sort of bringing anisotropy also to large-scale structure formation. All right, so with that, this is the final slide. These are my conclusions, and I want to also highlight this QR code that's going to bring you to one of my archive papers. It's not the paper I just mentioned, but it's a previous paper, but of course, still a very interesting read for that. All right, thank you very much.
All right, thank you. Any questions in the audience? Yes.
So I was a bit lost when you said that the shears and the vorticity are zero. Can you go back? Can you elaborate that? The shear, because first of all, the shear of matter you're talking about.
That's right, yeah.
Yeah. So how is that the shear is zero if you have an anisotropy momentum?
So,
I mean, I understand that you still consider perfect.
excuse me, can you repeat?
You still consider perfect fluid at this point, right? Q and pi are zero.
So pi is not necessarily zero in this context, actually, but Q happens to be zero. So the shear here vanishes due to a sort of a confluence of effects. One is that indeed I do assume that I have all scale factors being equal.
That's the point. There's only one scale factor.
There's only one scale factor, so that's...
in this x and y is a very special.
Yeah. So there is a, so it's very, yeah. So that's why the shear vanishes, but also what should be noticed that the shears that I also write that in my new frame that I've defined using these structure constants. So the shear in this frame with these structure constants is going to be finished. But the complication there is that a coordinate change or a general diffeomorphism is going to never bring it to a form where the structure constants do not vanish. So I cannot perform a diffeomorphism on these, on E1, E2, and E3, such that they become of a coordinate form. So even though it is indeed a tensor, this tensor is only invariant on the diffeomorphisms, but diffeomorphisms are going to keep it in the Bianchi 5 class and never bring it to sort of the standard coordinatization picture. So it is indeed a bit of a confluence of things that make that the shear vanishes in this case.
So when you were saying that you altered the Levy-Schmidt connection, is that in the sense that you lose the property of being torsion-free and having metric compatibility? Does that disappear?
No, so the Levi-Civita connection still remains. It is torsion-free and it is also metric compatible. But in order to make it be so, you need to add these specific terms. So if you now use this expression and you try and validate compatibility and torsion being free of torsion, you will see that it is so because you also need to take this commutator relation into account.
Okay, I think that's all we have to... Oh, go on.
Two very naive questions. First one is there a motivation why you choose the Bianchi 5 model?
It's a good point. There is no particular motivation for me choosing Bianchi 5 model. I could have also chosen different models to try and study for my example. Yeah.
And the second one is there motivation for assuming no scalar anisotropy stress?
Excuse me, so you mean to assume that pi is equal to 0 or?
Phi equal to psi.
Here. Right, yeah. So the reason, or it sort of hides the fact, that if you choose this condition, then you can more easily interpret this phi or this psi, if you want, to be coming from a Newtonian potential. Also because I have mentioned that my perturbation is in the Newtonian gauge. Even though I'm in the Newtonian gauge, I still have 2 degrees of freedom, whereas Newton only gives you 1, the potential essentially. So this second assumption sort of solidifies that I interpret this psi as really bona fide a Newtonian potential in a way.
Thank you. And that's all we have time for, so let's thank our speaker one more time.
Sure.
Cheers, thank you. So next up we have Levon Bogosian speaking. So I'm just going to get that set up now.
slow on the screen. Thank you. Okay, that's the.
So I just need to announce to those watching on YouTube that the video capture in the very small square had frozen a little bit. We're not going to not have a technical difficulty at least once a day. So that was that one. Hopefully that's it. Slides should have shown though, unlike on the first day. Anyways, that's everything. You ready? Have you got your mic on?
Yeah.
Wonderful. That's all working left and right. Fab. Thank you.
Okay. Thank you very much, Alexia, for organizing this meeting so well, and the other organizers as well. And also, just congratulate all of us on living at such an exciting time for cosmology. I think we all agree it's a very special time with a lot of interesting new problems for us to resolve. So I squeezed quite a lot of information into my talk, and I'll try to do my best to get through it. First thing I want to, we had a very nice review by Eleonora on the first day about the Hubble tension. So I don't have to tell you everything about the Hubble tension. I can just focus on one angle at it that interests me, which concerns the sound horizon. Do I need to click on the, yeah? Sometimes if I click and then do this, no.
It's the other click.
Okay.
There you go.
All right, thank you. So this is the plot that actually I think it's made by Eleonora, which groups the different types of determining the Hubble constant. And people often refer to the Hubble tension as a tension between early time and late time, something of that nature. I don't think that's necessarily accurate. I think the real tension, and by that I mean the 5 sigma tension, is between ways of determining the Hubble constant that includes using a model for the sound horizon and those that don't. And if you stare at this plot and look at every line in this measurement for a bit, you'll understand that indeed that's the case. So a key ingredient in this tension is the fact that some measurements use a model for example, recombination or model for physics at the epoch of recombination. So that, for me, is a hint that maybe we should look into what happens at recombination. So recombination is when the universe turns transparent, and there are sound waves in the plasma at the time which get imprinted in both the distribution of the CMB photons and the baryonic matter. And the size of the characteristic features is set by the sound horizon at the baryon photon decoupling. So it's the comoving sound horizon at the redshift of recombination. So there is some modeling that goes in determining the Z star. You need a theory of recombination, which is, of course, based on established physics. Then you need to know the sound horizon, and you need to know what H was made of, what components were contributing to it. Now, you can then determine H0 from CMB as well as BAO, primarily because of this very nice acoustic features, which represent the angular size of that co-moving sound horizon. So the CMB peak, it's perhaps one of the best measured quantities in science, not just in cosmology. It's measured with exquisite accuracy. It represents the angular size of the sound horizon. And so if you somehow know the co-moving sound horizon from theory, and you know the measured angle, you deduce the co-moving distance. And you can see from this triangle that if you had a smaller co-moving horizon, you would get a smaller distance. You would need a smaller distance, and that implies a larger H0. So one way to address the Hubble tension is to find a way to make the sound horizon smaller. Similar thing happens in the BAO, but before that, let me just emphasize that CMB measures much more than the angle. It gives you we have the whole spectrum, and even just from the temperature spectrum, not worrying about the polarization, which is measured to comparable accuracy now, we can constrain all the lambda CDM parameters. So matter, density, Radiation density we know from the CMB temperature, baryon density. And those are the 4 key parameters that you need to compute integrals such as this. And then you actually need a model. You need to have a module like recfast or something in your CAM code to compute Z star, and then R star is computed from the model, and CMB constrains everything you need to know about that model. So we have that very accurate measurement of the H naught from Planck, thanks to this.
There is also an assumed primordial spectrum.
And the, yes.
To be a power law.
Yeah, yeah. Thank you. Yeah. So BAO also measures, as I said, same physics, same angular size at a lower redshift, but of the similar sound horizon. So beta in my notation here is the inverse angle, and I'm only considering the transverse BAO measurement. So it's distance divided by the sound horizon, and you can measure it at many redshifts. BAO measured at 1 redshift gives you a band in this omega meta H naught RD parameter space. So you can see from these equations that there are 2 combinations that are constrained. But if you measure it at multiple redshifts, right, these bands now go at different angles and overlap, giving you quite an accurate measurement of these 2 numbers. So you can actually measure omega meta in the flat lambda CDM model just from BAO with quite a good accuracy. And you can measure this number quite well. Now, when you compare these 2 numbers that are quite well measured by DAISY to what you get from that full spectral CMB fit that includes the model for recombination, you get a tension. And Eleonora mentioned this as tension as the CMB BAO tension. 2.3 sigma is the most conservative one. If you include newer CMB data sets, the number is a bit bigger. So that tension that I'm pointing out here played a key, it's a key part in the claimed evidence for dynamical dark energy. So the evidence for dynamical dark energy is largely driven by this. Okay, so the question is it really necessary to introduce dark energy? So one thing you could ask, so what aspect of lambda CDM is actually in tension? Is it the expansion of the universe, something to do with the geometry background expansion? Like, do we need to modify recent expansion history? Or perhaps it's something to do with early universe physics. So let's perform a test. So CMB acoustic scale theta star is just another BAO point, essentially a transverse BAO point. And we can do the same thing we did with the BAO and plot that corresponding band in a omega meta RDH plane. If there was a problem with the model, this band didn't have to pass through it didn't have to pass through this oval, right? It could go to the side of it. And it passes smack through the middle. In fact, if you take the best fit W0 WA model and do the same thing, it doesn't go through the middle. Okay, it goes to the side, but the uncertainties in that model are so huge. You introduce 2 additional parameters that it's not worth even plotting because the uncertainties are big. But lambda CDM seems to be in very good agreement as far as the acoustic scale consistency test is concerned. Now, if you combine them, you get just the peak of these numbers, best fit values don't move, which shows very good consistency. But then you see this tension with the full CMB fit. Now, I did some studies, which I'm not describing here, with modified recombination models, and it's clear that if you allow for physics that can change the recombination and reduce the sound horizon, this CMB fit moves closer here. So it's quite possible and not problematic to reconcile CMB and BAO without changing any expansion history if you're prepared to have an open mind about the sound horizon. Now, let's try to find a way to measure the H0 without better than, like, try to break that degeneracy between RD and H0 without assuming something about the sound horizon. Can we do it? So one type of measurement that comes to the rescue is CMB lensing. So CMB lensing is a low redshift effect. It has a wide kernel peaking at around redshift 2. and it's largely insensitive of the BAO features in a distribution of matter. So it essentially constrains the matter density, the primordial amplitude, and if you are open-minded about neutrinos, you have to include them as a parameter as well. If you have a measurement of omega matter h squared, it breaks that RDH naught degeneracy in the BAO and allows you to actually measure the H naught. There is a remaining AS degeneracy, but that's actually quite well constrained by CMB if you only look at large scales, like scales constrained by Kobe. So you could optionally include a prior on AS that's conservative, that again doesn't vary too much, doesn't depend a lot on the acoustic peak range. And so we've done this analysis earlier, late in 2025, where we considered all of the available CMB lensing. This is a combination of ACT, Planck, and SPT lensing. We included the dark energy survey, galaxy lensing, and clustering, 3x2. Throw in the supernovae. Supernovae don't change anything about this result, but just for completeness, we put it in there. And then optionally, we put a Gaussian prior on AS, motivated by, it's broad enough essentially to envelope the models of different combination histories. And we find a measurement which, without this prior, we find 70 with a plus minus 1.7. And you see it doesn't depend much on whether you include supernovae, which is PP, or not. And then if you include that conservative prior on AS, you get 70 plus minus 1, which is quite interesting. So it's a measurement that does not depend on a model for the sound horizon. Now, it appears that sound horizon is a key ingredient in a Hubble tension, so it would be a welcome thing to reduce it for solving the Hubble tension, also removing this minor tension between BA and CMB, but it cannot fully resolve the Hubble tension. And this is something that my collaborators and I pointed out some 5-6 years ago. The reason for it is quite simple. So in this H naught, our sound horizon plane, you see the shoes band, and you see the BAO data. This is the old BAO data, but it doesn't matter. Now, if you try to reduce this, if you try to increase the Hubble tension by reducing the sound horizon and preserve theta star, then you have these lines. So each of these lines corresponds to a given fixed meta density. So at different meta densities, the lines are in a different place. But let's say you fix the meta density at the value of the current best fit lambda CDM, then you see you reduce the sound horizon, you increase the H naught, but you quickly exit the BAO band. And that's because these degeneracy lines, these angular scales at different redshifts give degeneracy lines going at different angles. So you cannot, at such a best fit meta density, you cannot have a very high value of H naught. At best, you can have something like 70 here, unless you prepare to make the meta density large, and then you get into trouble with S8 type measurements. So you violate bounds from clustering. So it's quite a simple geometric way to see why Hubble tension is not easy to solve fully by just reducing the sound horizon. Now, the Hubble tension has been a big industry for the last 5-6 years, and so many models were invented for the purpose of solving the Hubble tension. And I work on one proposal that I feel is special because it actually wasn't invented for the Hubble tension. It's a very old problem concerning the origin of magnetic fields in the universe, and primordial magnetic fields is one way to explain their origin. So very briefly, I won't have time to go over all the evidence for evidence for primordial magnetic fields, and I'm not personally attached to saying there must be primordial magnetic fields, but there is the circumstantial evidence that they would be welcome. So they are micro-Gauss level fields, so this should be a mu. In all types of galaxies where a measurement was possible, magnetic fields for the micro-Gauss are observed, and it's not impossible to explain all of them astrophysically, but a different mechanism is required often for very different types of galaxies. A primordial origin, like meaning magnetic field already embedded in the plasma at the time of prior to recombination, would explain all of them with one shot. There are other hints of magnetic fields in filaments over larger scales. There's a lower bound on the primordial magnetic field, meaning essentially a detection. Again, it's circumstantial, but it comes from node observation of GeV gamma ray halos around TeV blazars. So that's, again, quite an interesting hint. Again, doesn't have to be primordial. It's over very large scales, but it's at low redshifts. And so anything that's not in a CMB technically could be astrophysical. And maybe we just haven't found the right astrophysics. On the other hand, you could say, well, magnetic fields must have been produced in the early universe. Forget inflation, because I think that's sort of more of a designer approach. But let's just take phase transition. The electroweak phase transition has Higgs. During the symmetry breaking, Higgs has fluctuations over spatial fluctuations. There are gradients in the Higgs, which eventually decay. And that all that energy in the Higgs goes into surviving fields. And one of the surviving fields is the photon field. So some of that energy in the Higgs will remain in electromagnetism, and there will be magnetic fields. And the question, therefore, is not whether magnetic fields were produced in the early universe or not, but whether enough of them were produced and of the type that could be relevant in the current universe. So very briefly, magnetic fields, so the idea is that they would be produced at some early time. Once they are produced, they have the property, and they would be stochastic. And it's not like a uniform magnetic field. It's a random tangled magnetic field. There's no uniform component to it. So it's stochastic. And once produced, it would remain frozen in the plasma, meaning when the plasma flows, magnetic lines flow with it, okay? And as the universe expands, photons, magnetic fields are just part of the radiation density. So we know radiation density goes 1 over a squared, and it's also b squared is radiation density. So b magnitude of the magnetic field just goes down as 1 over a squared. And we characterize such stochastic field in terms of power spectrum with some exponent n. So if they were generated in something like a phase transition, like the electroweak phase transition, there's a very robust prediction that this n has to be 2. It's based on causality arguments. And then inflation opens a can of worms. You can have anything you want, but there is no known working model of magnetogenesis as far as I know. Simplest models predict its scale invariant. The current bounds on such magnetic fields range from the BBN. Yep. Am I okay on time?
We are running over.
Oh, okay, sorry. I'll
summarize it.
Okay. So if you wanted to, sorry. So there is all these bounds. Here you have the magnetic field strength on a given length scale. And this square here is what you would need to explain the magnetic field of the Milky Way purely from the primordial origin without any dynamo. So you need something like 10 to minus 10 Gauss on kiloparsec. And both scale invariant and phase transition fields represented by these lines would be enough. So let me now tell you briefly, very briefly, why magnetic fields relieve the Hubble tension. So magnetic fields are inhomogeneous, and they, as the universe starts to turn neutral, baryon inhomogeneities are allowed to develop in response to the magnetic field. So inhomogeneous magnetic field push baryons into regions of lower magnetic density. And inhomogeneous recombination results in a faster recombination, therefore a smaller sound horizon. So this effect can be represented here. It's very simple in a recombination rate equation. You have an n square, and because you have an inhomogeneous distribution, average of a square is larger than the square of an average, so that is enhanced and recombination goes faster. This was pointed out in 2011, resulting in ionized fraction versus redshift shifting to an earlier to higher redshifts, and that results in a shift of the peaks. Okay, and we showed that this could relieve the Hubble tension in 2020 using a toy model with my collaborator Karsten Judamzik, and that was the same model used in 2011. Since then, Karsten, primarily Karsten in collaboration with Tom Abel and Ali Hamoud, performed MHD simulations demonstrating this effect. Without a toy model now, it's actually in MHD. And we put it into cosmological codes. And we find that, amazingly, this proposal is not ruled out. I say amazingly because CMB is extremely sensitive to the detailed shape of the ionization history. One wrong wiggle, one wrong turn, and it's ruled out. Amazingly, it's still not ruled out. So we get something like 70, H naught of 70 with a magnetic field at present time of about 0.01 nanogauss. So at recombination, it would correspond to something like 0.05 nanogauss. And that's smack on where you would need it to be, so it's quite intriguing. And it's a highly testable proposal, okay? In the worst case, if it gets ruled out, we'll constrain a magnetic field to the point where nobody will be talking about primordial magnetic fields for a long time. It's an extremely sensitive feature, and it's amazing that it's still alive. Our main limitation is the MHD simulations. The variance in the simulations is too big to match even the precision of ACT and SPT today, so we're working on getting that better. So high resolution CMB temperature, the silk damping tail in particular is the most constraining feature of this model. We'll see how it works out. And then there are all these other ways of testing it. The nice thing about it is once you see, let's say you see a detection in CMB, you have a clear target and you can go after it with all kinds of other ways, gamma ray astronomy, spectral distortions, and if you don't see it there, then you know it's something else. Okay, so now how do I, okay, and to conclude, so Hubble tension hints at something missing at the sound horizon, and maybe magnetic fields have something to do with it. It can only improve the Hubble tension up to about 70, but the point of it is that magnetic fields, even if we detect them without solving the Hubble tension, is still a major result, and the amazing thing here is that they haven't been ruled out so far. And we will find out in a very reasonable amount of time, let's say within 5 years, whether it works or it doesn't. There is no model freedom in this proposal. Thank you.
Unless there are any burning questions?
There's a very quick question. 0.101 nanogauss on what scale?
We assume a spectrum. So in short, it's the total magnetic field energy. So it's total B squared, square root of the total magnetic field energy. In a way, it doesn't really matter. But for us, what really matters for this effect is how much magnetic strength there is on kiloparsec scale at recombination.
The TeV gamma ray crisis you referred to, is this adequate to explain the absence of low energy gamma rays from TeV blazars?
It's within the margins. Yeah. Yeah, and that's one day they will meet. So yeah.
Oh, yes, okay, last one.
You mentioned generating the primordial magnetic field in phase transitions.
Yeah.
Phase transitions, of course, happen very early, and the horizon is extremely small. So your magnetic field will be extremely incoherent. I mean, you have a paper of Ruth Turer mentioned. It actually supposes that there is an inverse cascade mechanism. Boost that enlarges the coherence length. But in order to have an inverse cascade mechanism, you need a helical magnetic field. So this is a very particular requirement, which is not guaranteed in general in phase transition.
You're absolutely correct that having helicity helps with the inverse cascade. In the last 4 years, there was a new development, a new conserved, so it's because helicity is a conserved quantity. There's a new conserved quantity that's been discovered called Hosking integral, which allows for inverse cascading without helicity. So it's work by Hosking and Shekochyhin, also actually from Oxford. Yeah, Alex Shekochyhin. So this generated a lot of excitement in this phase transition induced magnetic field community, because it actually, one of the papers they wrote pointed out that this conserved quantity makes it possible for magnetic fields to survive without helicity.
Yeah, but you have to generate helicity in the first place, in first transition.
Sorry, but?
You have to generate helicity in the first place.
Helicity will inevitably, like fluctuations of helicity, maybe not global helicity, but fluctuation of helicity will be generated. But Hosking integral doesn't need helicity. It's a line, magnetic field line linking conservation type.
Specifically,
yeah.
The mechanism you suggested, Vachaspati, is
yes.
You don't actually need a phase transition. The electric
Exactly. It's the
but it's the dumbbells, the temporary topological structures that form in the Higgs field that will give you the.
It's not even, doesn't even have to be topological.
But these are not topological.
Yeah.
These are
Yeah. Yes. So it's actually. It's yeah. I'm working with Vachaspati on this as well. So we can see fluctuations in gradients in a Higgs field, which inevitably are there. So having a stronger phase transition helps. But even if it's a crossover, there'll still be fluctuations, and there'll still be some magnetic fields.
Okay, thank you. If that's all, we'll thank us So now we have a break to do some posters, but we're also going to use this time to do a conference photo. So try not to miss that. And then we'll be back with the conference summary. We might start maybe about 12:05, just to make sure we have enough time for posters.
Where?
The photo, Derek, sorry, where will the photo be taken?
We'll use the foyer just outside.
Yes, the foyer outside. Thanks, Al.
thanks, folks, for being moderately well behaved for the photograph. We're now very pleased to welcome to our meeting our Pro Vice Chancellor for Research, Professor St John Crean, who's just going to say a couple of words.
Thank you very much. A couple of words to a group of cosmologists is a dangerous thing, I think, so apologies. I'm here to say thank you. Thank you for all of you coming to this event at the university here in Preston, University of Lancashire. Perhaps not the normal venue for such esteemed academic events, but I think it's a significant reflection of the appetite within this university. I was explaining to Joe that we're a university that's almost 200 years old. 1828 was the first time the university appeared on the education world as the Institute for the Diffusion of Useful Knowledge. Let's hope that continues to this day. We think it does, despite what the government is trying to do to us in all sorts of arenas, mainly by mentioning that they only ever mention the word skill in this country. They rarely mention the word qualification. So you can see this is a challenging arena. The university has north of 35,000 students, of which around 23, 24 are centred on the UK. It's an evolving university that's attempting to maintain, in amongst its educational responsibilities, an interest and a growth in research. We have, as many of you know, the Ivy League or the Russell Group universities, which quite rightly have earned their reputations around focus and commitment to research. We have similar ambitions. We are currently research focused. We are increasing our research activity relative to our, proportional to our staffing base. And I think it's a testament to that ambition in the research arena that individuals like this young woman have emerged from PhD programs and appear to be on a track towards some serious notoriety or influence, probably a better word, in the cosmology world. And Alexia is a good example of, we have a number of individuals whose ages I daren't even think what age she might be. But we have a few, 4 or 5 others around the university who we have promoted to lead the vanguard of the successional events that take place as individuals of my age, for example, naturally fall off the tree. Events like this are not insignificant to us as a university. The Vice-Chancellor, I think, came on Monday to give a talk around his appreciation, and we've been discussing it. To have individuals of the reputation, such as Joe and Penrose and other colleagues, is extraordinary. But all of you are contributing to an environment which we hope will continue to push forward. I'm a trained surgeon. I've got nothing to do with the world that you guys live in. I recognise that there are numbers, I just don't know what they're telling me. But when I moved up here for a short while, I lived in a place called Muchhool. Muchhool is around 4 or 5 miles out of here, I think sort of eastish, southish of Preston, and I knew nothing about it. And I had my head in other projects, but I kept getting these mildly threatening emails from a chap called Ward Thompson. He kept going on and on about something called the Jeremiah Horrocks Institute. And these emails were relentless. That's Derek's approach, by the way. He's relentless. And these emails kept coming, and eventually landed on the fact that this chap, Jeremiah Horrocks, who lived some time ago, based himself in a place called Muchhool, or just north of Penworth. And I, in fact, then turned out that I lived next door to the Muchhool post office, where much of his parents, I think, did some of his work originally. So he said, "You've got to go to the Jeremiah Horrocks Institute lectures." And I said, "Oh, leave me alone, will you?" And I did go to the Jeremiah Horrocks lectures, and to this day, they are the most populated public-facing lectures this university provides, other than having to offer free money to get people through the front door. Must be, on average, we have around 150, 200, sometimes north of 200 in a big lecture theatre. And they're mesmerising. I understand maybe 60% of what's being said, that's fine, but the presenters that I've met and I've listened to have been extraordinary. In this room is enough intellect, I hope, to drive your area within the university sector, to continue to drive it. But there's a bigger plea, and I was suggesting to Joe, tongue-in-cheek, about the importance to the human race of the work that you guys are doing. We live in a very turbulent world, and uncertainty pervades throughout and beyond lifetimes in this room. Perhaps some of the answers lie in some of the work you guys are doing. And as a group, I applaud you for that, and I wish you the best on the rest of your journey. But for the moment, Alexia, colleagues here, thank you very much for your time this week, and I hope the rest of the week, the rest of the day, continues in the same thing. Thank you very much indeed. Thank you.
Thank you very much, St. I'm sure I wasn't that pestery at the time.
Yes, he was.
I'll hand you back to Lexia for our final science session of the week.
Thank you. And yes, thank you as well, St. John, for that great few words. That was really kind. So, yes, we have reached the end of our conference. So I now invite Professor Joe Silk to come up and speak on the conference summary.
Okay. So thank you, Alexia. So first, thanks very much to all the organisers. It's been a really fascinating conference here, addressing, you could say, the battlefront, really, in cosmology. They're the area where there are fascinating controversies. You look for the cracks in the structures to learn more about improving your foundations and structures. So we'll see. Anyway, let me begin. It's been difficult to do a summary because it's been diverse topics, but you'll see I will try to give you the general flavor of what we've heard. Okay, so here's the big picture of the universe. We're basically here today, surrounded by this wonderful universe of galaxies, and light from the past comes to us, and the furthest back we can see directly is about 400,000 years after the Big Bang, where we see the microwave background radiation with various ripples, fluctuations in it, slightly hotter spots, slightly colder spots, and this provides an image of the initial conditions from which all structure later began. And so the more positive, hot, slightly warmer structures here, really just temperature fluctuations in the radiation coupled to the matter and indicate the presence of gravity, which then eventually leads to the formation of stuff, of galaxies, of stars, everything else, by this process we call gravitational instability. Well, that's all wonderful. We don't know much about the beginning. This dramatic phase here, this is the Big Bang, and we see this exponential explosion. We infer that, actually. I won't say that we see it. It's our best model for the universe. And so I've added the big uncertainties here. So we really conjecture about the beginning. It's a nice model that leads to explaining much of the present structure. We'll discuss some of the cracks in it. We have been doing that this week. But by and large, it looks pretty solid. As you go forward in time, when the universe expands to its present size, and then the radiation basically decouples. All this hot radiation then stops structure from forming, but at some point things cool down, and then the matter, can freely develop structure, the ordinary baryons or whatever else there is. And so there's a big question mark here about 50 million years after the Big Bang. We call that the Dark Ages. We haven't seen it yet, but it's the target, it's the new frontier in astronomy, which I'll describe later on in the talk. But that's basically just hydrogen clouds, the building blocks of galaxies. That's what we hope to find. We haven't seen them yet. And then there comes a point when all these structures develop into the galaxies that we see and love. And today, I would say, the biggest question we have today is, are any of these stars there, with many were known to have planets around them, is there life anywhere else? Are we alone in the universe? So these are the principal questions, the beginning, the Dark Ages, and are we alone, that we have in our science of astronomy and cosmology today. And I'll try to give you some inklings. I won't say much about the are we alone issue in this talk. You can hear more about that later this afternoon when I give the colloquium. Okay, so the microwave background. It's had incredible progress in the past 50 years. So when I sort of, some tens of years after I began in the field, this was the story basically. There was basically there was dark matter that it was evolving with time, and these are density fluctuations growing in strength. And there was radiation that sort of connected with the baryons. It was like sound waves basically, because of these are pressure waves. The radiation pressure was so high that you can think of it as sound waves. And then at some point the temperature drops when the universe cools down sufficiently for the baryons, protons, electrons to recombine and leave you hydrogen. And then the self-gravity leads to development of fluctuations into structures. And we look for these ripples in the radiation as the imprint of the proof that all of this happened in the past. And so amazingly, it took about, from the earliest predictions, 30 or 40 years actually. But then at the end of the last century, we got to this point where there were fluctuations, mostly in balloons, some on the ground, looking for tiny ripples in the background radiation that were the seeds of today's structure. So that's how things were, in 26 years ago, and this is where we are today. So the big change today has been that we have had satellites. So the first one was launched in 1990, that's the COBE satellite. Then a decade later, there was the WMAP satellite, and most recently, 8 years ago, the Planck satellite. And you can see they have increasing resolution. More and more powerful telescopes are involved to look at the microwaves from the early universe. And so this is our current map of structure with the temperature fluctuations. And if you project this structure to basically a power spectrum and look at the fluctuations, then this is a measure of the fluctuations. You see this, these basically fading away because of the effects of the radiation on the fluctuations, smoothing things out. But these are signals of the fluctuations that lead to, with remarkable precision. The main thing you must note is that this reproduction of the sky maps in terms of temperature fluctuations has incredibly tiny error bars, right? And so the red line is the prediction from this very simple model of basically sound waves suddenly freezing out and giving you an imprint of what happened 400,000 years after the beginning of the Big Bang, which is essentially what we're looking at here. So this has been the basic reason we believe in the simplest cosmology, which predicts this. Of course, we don't know what happened at the beginning, but this is today's estimate of the incredible precision we have. So that's the, so we're trying now to see where to go next, okay, with all of this. Okay, so just the other thing that comes out of these satellites, so let me just show you close-ups of the two major satellites in the past 20 years that have basically led to this discovery. And so they not only give you this map of the temperature fluctuations, this of course is the outline of the Milky Way, the dust, most of the dust in the Milky Way galaxy, which we have to basically muddle to extract this information, but that's story. So here are the temperature fluctuations. We also measure the polarization of the light, and that's very interesting because that tells us about things like effects of magnetic fields all around us in the universe, and ultimately is a source of the fluctuations from the very beginning in this period of inflation that predicted a certain primordial polarization, which is marked, unfortunately, by all of the galactic stuff. But nevertheless, if we could ever get down to that, that would be a direct proof of inflation. So I'll come back to that. And then finally, the effect of dark matter in the universe distorts slightly the radiation because of the effect of lensing of the clumps of dark matter in galaxies and clusters of the background radiation. And so by looking at these distortion-produced signals, which are also polarization, you can infer the dark matter distribution too. So all of this comes out, magnetic fields, dark matter, and the seed fluctuations are all buried in these amazing maps that we have today. Okay, so, the remarkable thing that gives us great confidence in the phenomenology of the cosmology is that we can describe these amazing maps by basically 6 numbers, which describe what we call the lambda CDM model, lambda standing for the cosmological constant that Lemaitre first invented and Einstein initially hated, but I assume, but modern cosmologists come back to follow this now, which is a late acceleration of the universe. That's what it gives you. Anyway, and we measure these numbers, which can reproduce all of the details of these maps, all of the structure of the maps, with basically 6 numbers, which we measure now to incredible precision. Okay, so the big advance then has been towards precision cosmology, which we've talked a lot about this week. However, the problem is, and let me take a slightly more philosophical view here, that we're great at precision and we're going to do better and better in the future. It's easy to imagine bigger and better experiments. The only problem is they cost more and more, so at some point there is a limit. But the real issue is, what about accuracy? Are we basically looking at the right place? And so it's this story, basically. You can have incredible precision, but you might be missing the target of your bullseye. And so that's what we basically are aiming now to understand better. That's what this meeting has been about, really. What could we do to do better in terms of accuracy? And essentially, we're sort of at a crossroads in cosmology, I would say now, where there are hints. There are cracks, if you like, in the edifice. But, you know, can we just plaster them over? Or can we just continue? Will there be signs of something more fundamental coming? We at the moment, it's an interesting time to try to decide this. And basically, we need bigger and better experiments, or more accurate experiments. And I'll explain how some of that might happen in the future. Okay, anyway, so another way to put this is that we may be running into this trouble, is that in terms of statistics, for physics, if you want to discover something, you need to be 99.99 confidence level. We call that 5 sigma, basically, evidence for something to be a new discovery. Now, I should warn you that 5 sigma, although all of my colleagues accept this as the evidence for a new discovery at a big particle accelerator or something, or in astronomy, it's a wonderful thing. I have seen in my lifetime even a 10 sigma experiment disappear because of unknown systematics that cause it to go away. Now, that may be a rare event, but that happens too. So one has to be very, very cautious. And no one is funding experiments that can give you 10 sigma results. That would be so expensive or amazing. We go for 5 sigma basically in physics. And so it's not easy. Let me show you one example that we've talked about a lot this week. This is the DAISY results. And so this is the latest dark energy survey, which has argued that this lambda component, what we call the dark energy of the universe, it varies with time. And so you can see this would be a fundamental difference from the Einstein, Lemaitre, Friedman cosmology that we've been working on for these many years, where this lambda was a constant of almost a paradigm shift in our fundamental, if it's correct. Okay, but the problem is, look at the error bars. So shaded in light blue, these are the 2 sigma error bars. This is going back in time with redshift. So clearly, you're a long way from a 5 sigma detection of variation of that, but maybe better experiments will help us. Okay, so let me talk about this wonderful microwave background map, incredible precision. This has led to really, and those 6 numbers I mentioned, we measure with 1% precision, almost all of them. And that's an incredible change from when I began in cosmology, where we were talking about 50% uncertainties in many things. And you know, this was only 30 years ago, actually. So things have come along a long way, okay, in this time. So there are now, when you look in more detail at these maps of the sky, there are anomalies, okay?
So I want to take you through some of these anomalies. We've had whole conferences about these anomalies. In some senses, this meeting here has considered this in some detail too. Subir held a meeting in India last December, which I couldn't actually go to, all about anomalies, for example. Anyway, so what is there? So here is the power spectrum of these fluctuations, and the solid line is the prediction of the phenomenological model, the lambda CDM model, the canonical model that we also, most of us swear by, and all the observers try to measure with higher precision. And we look for interesting hints that it might not be right. That's the way you have to attack these problems. And so when you stare at this map, you see all the error bars from the data, and you notice there is one error bar that stands out like a sore thumb there. This is the quadrupole anisotropy. This is going from large angular scales to small angular scales. Here we're down at the arc minute level, and this is the many degree scale. And you can see the quadrupole, which is half the sky, fluctuations of order half the sky basically, there's a huge error bar, but the mean is very low. But again, you stare at the error bars, it's clearly not a 1 or 2 sigma anomaly, right? But it is a worrying when you look at that. But that's not the only one. So we've now been studying other anomalies with all this high precision data. So this one is maybe one of the most interesting ones. You find there's some weird spots in the sky where there are excesses of the blue stuff is excess temperature, the yellower stuff is deficit temperature, large regions which are not really predicted in the standard model. But are these just statistical fluctuations, or is there something real hidden there? Well, again, we don't really know anything more than at the 2 sigma level. So so this has been a study of these. So this is one of the anomalies, the hotspots. There's a north-south asymmetry. There are various others in the sky maps, and so this shows you, I think, five of the other ones. And this shows you that basically you're on the tail of some distribution. In almost all of these cases, right? Depending on what cuts you do on the sky, that's the main variable here. And so, again, 2 sigma-ish effects, 2 sigma-ish, that's what they're all claiming. And since they look at, now if somehow you could wave your wand and say, look, I have 6 different 2 sigma effects, I add them together, I get an amazing effect, that you simply cannot do, because we just don't understand the correlation between these different anomalies on this one sky map that we have. And so we've sort of been stuck there for a little while, I think. And in some sense, we all worry now about what this all could be indicating, but there's absolutely no solid proof that there is anything wrong. But one has to be careful about this, of course. Okay, so to summarize, there are some 6 unexplained anomalies in the microwave background, which is our main precision cosmology tool and glimpse of the very early universe. 400,000 years after the Big Bang, and should we panic? And my answer is very simple: no. Okay, so that's one of the stories. Let me show you one last word. I can't resist this because of this conference on CMB anomalies. So this happened in 2010 when we got the first high precision satellite, WMAP satellite. This is 1 year of satellite data. You can see all these wonderful fluctuations. The Planck eventually confirmed. And then, look at this. That data revealed, now look carefully over here. Can you see the initials SH? Yes, of course. So this got a lot of attention at the time. Just what the hell was going on? And then other people said, well, here I can see Phoenix, a donkey, a parrot, whatever. So the human eye can see strange things. So, I think no one would take that seriously. Okay. So let me then summarize the tensions, the main tension that we're facing now in cosmology, which is the Hubble constant. That's the expansion rate of the universe. So some of my colleagues in Johns Hopkins, Adam Rees in particular, Nobel Prize winner, is one of the leaders in this pursuit of refining our measurement of the Hubble constant. And he's coming up with a value with his group and his procedures that lead to a major difference with other groups that focus basically on the precision cosmology of the microwave background, use only that. In principle, those parameters that I showed you from the sky maps 400,000 years after the Big Bang can give you directly the expansion rate of the universe, essentially from the angular scale of what you're looking at. It comes out basically from that, but that number doesn't seem to agree with what Adam and all of his colleagues measure when they look at the nearby universe using distance indicators, so-called standard candles, that range from Cepheid stars in the very nearby universe to eventually supernovae, which are also thought to be standard candles further away. And so he comes up with a significant tension, you could say, between two measurements which each claim high precision, but there's a difference between them at 5 sigma or more. Okay, and so many theorists, especially in physics, have jumped on this because they're always searching in the high-energy physics community, who do a lot of cosmology too, for solutions to any interesting, which may indicate new types of physics that so far we haven't encountered. And that's, you know, the holy grail of physics, to find some new particle, some new theory. This might indicate something new for cosmology, really important. So what you conclude at the end of the day, that maybe you do need some unknown new physics which may help you break this dichotomy between what we get from the early universe microwave background, what we get more locally. You know, maybe something is changing that we don't have control of yet in physics, or the data is a problem, because what we use, especially when we use the conventional techniques in the nearby universe, we use what is called a distance ladder, which involves going from the nearby stars, which are wonderful distance calibrators, and we then look for them in galaxies further away. They're exploding stars, supernovae, which also are great distance calibrators. And then finally, when you go further away still, you see only the supernovae. So that's the distance ladder. And basically, you're combining different data sets. And you worry that there might be systematics that you really haven't got full control over. So that's the counter argument. There's something incredible going on in terms of new physics, or there's a data problem. Okay, so that's one of them. And in the past couple of years, a new one has emerged. And you know, when you get a new tension, that does make you worry even more. And so the new one is called lambda, the metric constant dark energy is how we interpret it. Does that vary with time? And there's a data set, which a wonderful data set called from the DESI survey and previously the DES survey, dark energy, so D is for dark energy. And those surveys of millions of galaxies indicate a possible time dependence. I showed you one example of the huge uncertainty in that, but that's sort of maybe at the 2 sigma level. Okay, the problem is that it involves calibrating again on different data sets, this time of galaxies, where you have to worry a lot about systematics. And I would say there are a number of papers out there saying systematics may dominate, others claim it could be a true effect. And of course, the physics community gets very excited. This is yet another way to try to constrain some new theory of physics, which this is not predicted by a standard model of the universe, of course. Okay, so my summary statement to all of this is that there's no even mildly compelling new physics solution in sight. Okay, so all of these possible solutions from our physics colleagues, who are in fact far more numerous than we astronomers are actually, and so they have a huge say in a lot of this, especially in the funding, is that they have failed so far to come up with anything compelling. All of the possible solutions they have, which might involve different dark energy at early epochs from today, etc., various complicated things, none of them solve the problem. They all, they don't make things worse, they do make things better, but they still leave a problem behind with the Hubble constant tension, for example. Okay, so what do we do? Before I tell you what we do, let me describe the tension that's been one of the themes of this workshop. Okay, again, so in the early days of cosmology, you know, we had these surveys. This was the pioneering survey. CFA is Center for Astrophysics, 1,000 galaxies, different redshifts. This weird distortion is from distortions, of course, in redshift space. So really, this is a cluster of galaxies, but with random motions that stretch this out, since this distance scale comes from random motions. And then, you know, simulations were done even before this data, and they could reproduce these structures, interesting structures, and reproduce much of this. So this was the epoch of, you know, and this seemed to fit the standard model that we had of a cold dark matter model. Things got better over, again, it took decades, but this was the 2-degree field survey done with the Anglo-Australian telescope of 250,000 galaxies, which was sort of a pioneer to the modern age. And what is interesting, I want to highlight this figure here, is you see you use redshift as a distance indicator, so you project in redshift space, and one of these is simulations, and one of these is the real data. So simulations of a large box on a computer in the standard model, and you can see it's very hard to, you can tell this is the real data because you see this stickman effect, which is an effect of redshift. So you can see that in the real data, but in the simulations, you know, you can imagine if you had enough simulations, you'll see things exactly like this, but qualitatively it looks exactly the same. Okay, so that I think was not determining what happened next. So this is the latest, okay, from earlier this year. So now we've moved up to 47 million galaxies, okay? So this is dramatic, and you move out again in redshift, okay? Going out, higher redshift, and this is a sample of the local universe. And what you can see is that, to me, things look much the same near as they are far away. There's no obvious major difference. So qualitatively, it's more of the standard universe, the standard cosmology. Now, again, we still are in the process of analyzing this data in gory detail to look for tensions. So far, I don't think any tensions have been found, and this is just showing where we're going, really, but with current data in hand. But there are no obvious things jumping out at you saying that we've got the model of our universe wrong, because it looks much like the, you know, the earlier simulations, this sort of thing. Yeah. Anyway, so let's move on. So I think it's important to celebrate the success of our current theory. These past 2 days here have partly been, you know, in finding, as I said, cracks in the edifice of our current theory, but what is it good at? Okay, and so here is the great success of our theory. It can take you from the small scales that make the galaxies, the effects of gas clouds breaking up into stars, exploding stars, all the way up to the larger scales with numerical simulations using the largest computers we have. And so this is a picture of how well we've done. And I want to say that there are several different large groups of cosmologists around the world, in Europe, in the UK, in the US, etc., who are doing these numerical simulations with millions, with billions of particles, actually, in their simulations. And they can do an amazing job of reproducing galaxies, okay? And so these are artificial images of galaxies. And you can't really tell the difference when you stare at these from the real thing. Some of my colleagues will say, well, maybe some of their disk galaxies are too thick, whatever. Anyway, it's all being debated. And so, and then these simulations, and they have, you know, Illustris, Magneticum, etc., Eagle. You can see they all make very nice pictures of the large-scale structure of the universe, and even larger scales, right, reproducing the surveys I showed you. You can see all of this comes from simulations with these boxes that are now up to megaparsecs, hundreds of megaparsecs. The weak link, of course, is in the physics that goes into this. Simulations that simulate large parts of the universe are unable to look at the compact structure that goes into black holes or exploding stars, supernovae, massive stars without flows, you know, all this astronomy stuff, which they put into sort of a black box, a model, you know, and use that to make their large-scale maps. That's fine. And what maybe not everybody knows is that when they do this, you know, we have half a dozen groups out here. They do not agree with each other. That there are serious issues, and what we call the subgrid physics that you can't resolve numerically is the problem, and that's still a big debate, and we'll probably only get better by using more and more powerful computers. So it's the way we'll be going, but the answer is we are not there yet in understanding the details of massive black holes and stars and everything else. So that's sort of the problem we're at there. Okay, so what do we do? Okay, so let me give you my philosophy on this. So what we could do is say the current data is rubbish because of these systematics, right? So that's one possibility. Well, let's consider another option, okay? So this was advocated by my George Stelly, my colleague at Cambridge, and the idea is you just park the data, right? You wait for something better to come along. So what is he parking here? Well, it's dark matter. It's why the cosmological constant is whatever it is, which is unexpected, the inflation, whatever that is, the potential inflation. And here, of course, he wants to park the Hubble constant problem. Okay, so that means we wait, we get better data, and maybe we'll do better. And then finally, there's the hope of my colleagues, new physics, in particle physics, and then, of course, after a decade of searching for this, not even the slightest hint that we're on the right track to anything. Okay, I would say. So that's sort of, yeah, a bit disappointing, but that's where we go. Okay, so now let's get back to this very specific meeting. Here are some of the amazing things I've seen this meeting. So I've been very impressed by, you know, Alexia's giant rings on the sky. These are galaxy points, of course, over now hundreds of megaparsecs. Some of these you can see on similar scales in the nearby universe. This is in the distant universe, this is nearby. We may be surrounded by similar shells and these quite amazing structures in the sky that we heard about, and individual structures that might correspond to the baryonic acoustic relations, which are, you know, I showed you earlier, predict fundamental predictions of the theory. Okay, so all of that looks great. I mean, I don't think we're there in terms of confirming any of this. So I have one suggestion, which I think is important to look at for confirmation eventually. And this was a hint from the paper by Andras Kovacs. And you can see he showed us what happens when you stack 50 clusters together, where you know the obvious structure, and you compute the effect on the microwave background, which is called the integrated Sachs-Wolf effect, due to the variation of gravitational potential along the site. Okay, and that gives you, you know, temperature fluctuation basically. And so that's been measured over the whole sky, of course. But what he notes is that here's what you predict for your stacked 50-odd clusters or void. He does similar things for voids, and you observe something larger. Okay, and it's, you know, 2, 3 sigma, whatever. And it has to be confirmed. And where does this come from? Well, normally what you measure with the CMB are what we call the curvature fluctuation. So the relative potential is just gm over r squared. This is the excess mass in a fluctuation, and delta rho times the volume. And you can see this should be gm over r, apologize for the typo. And so that scales as r squared, fine. But this time-dependent effect, which is interesting for large structures, is the variation in potential across the line of sight. And you can see that scales as r cubed, the size cubed. So it's a wonderful way, I think, for tackling the reality of the giant rings. And this is sort of a message for Alexia, really. And you basically have to look for, since you know where to look, where you see a giant ring, you then have to do a convolution with a CMB sky and see if there's any excess fluctuation. And obviously, with a lot of work on the look elsewhere effect. So that's one suggestion, that may happen. Okay, let's talk about one more anomaly. So this is Royers from this morning. To me, this is very striking. So it's the dipole. The dipole agrees in position with when you look at the quasars, but when you look further away, there's an offset in amplitude. Okay, so I think I do have a preferred explanation for this. It's a super horizon scale fluctuation that's pulling us. This was suggested many years ago by Michael Turner. And here's a paper in which they actually use this to show that this could be a viable explanation by Royer and others, Subir and others, also Subir. Okay, so nothing much has changed. This is an option, but actually one thing is new, and that is that what can cause such a large isoconventional fluctuation, there is one thing that we know that does produce these, and those are ultralight axions. And if you have axion fluctuations on very large scales, that could do the job too. That needs more detailed study, but the reason we have more confidence in this option now is that there's a phenomenon called cosmic birefringence, which is the rotation of the polarization of the microwave background, not predicted by theory, but detected now at the 3 sigma level, and the ultralight axion might be ideal because of its coupling of magnetic to radiation propagation properties for producing something like that. Okay. So now let me go over the next stages in how we're going to try to address some of these anomalies. So the microwave background, CMBS4 was cancelled, as you all know. This is the Simons Observatory in Atacama. We expect the final results by 2035. So their target is the tensor to scalar ratio, which is the prediction of the inflation theory. There should be a tensor gravity wave component, primordial one, and they'll get to a sensitivity about 30 times or so larger than we have, better than we have now, 100 times larger roughly, of 0.001. And they have, a number of telescopes and looking at 6 frequencies that have detected. So that's one experiment that is going ahead, wait 10 years. There's another experiment which is expected to launch around the same time with a similar goal, and that's a space experiment funded by Japan called JAXA with strong, called Lightbird, with strong European participation that will go to the L2 orbit where the Webb telescope is. You need fewer detectors when you go into space because space is so much more efficient an environment to have the microwave background. That's why one gets away with a small number of detectors. Anyway, so that is scheduled but has obstacles to overcome. Okay, so how do we use this new data to tackle inflation? So that's the big question. That was my early question mark, remember? One of the biggest mysteries in cosmology. So the answer is we have to basically clean up the microwave background. So here are the temperature fluctuations. Here are the E-mode polarization fluctuations produced by intervening stuff such as basically dust scattering and other things as well, and lensing, of course, of dark matter. And then finally, the B-mode fluctuations, the curl mode fluctuations in the polarization. And again, there's a major contribution from lensing. But when you get down to the lowest angular scales on the right, you expect to see peeping through the primordial component. Okay, now you notice here is an indication in the dashed lines of the prediction, and this is for a tensor to scalar ratio of 10%. And we've seen nothing. And the idea is to improve this by 2 factors of 10. And so who knows what we may see. And over here you have the one experiment that is destined to do this most directly, the class experiment at Atacama, and that is way above at the moment, but will be getting better. Okay, so those are, that's the story there. And then here is the problem with this all. So these are the inflationary models that we're aiming for in terms of this ratio of tensor to scalar mode. And so this is, 0.01 is roughly where we are now. And this is all the possible, so the shaded stuff are the current limits. And then here are all the various models. But the point is this, you can see there is no lower bound, okay, in the models, basically. So right now, we're projecting, going down to tackle some of this parameter space. There are models in here, in the parameter space that we have at the moment, and we're going to increase all of this to some lower level. But there's no lower bound, which means we have no definite prediction of what we might find to test inflation. And if you were to be a Bayesian advocate, you'd say they have a very small chance of success, given the parameter space that's waits ahead. And so this was, how, I think Penrose put it too, that inflation is the big question mark in cosmology, but one of the greatest challenges to get there, and I don't think it's unlikely, if we're lucky it might work, I think it's unlikely to be the CMB. So let me now just briefly show you the future, where we're going in cosmology. So basically the problem is that for dark energy, we have all these wonderful experiments. The newest one, I don't think if you know about it, it's the private space telescope funded by the Schmidt Foundation. We're all designed to detect supernovae, constraints, and you can see we're zeroing in on the standard model, but still with security error bars, and there's no indication we'll find something interesting physically. Microwave background, I just went over the problems there, so our current prospects are satellite and 2 observatories, one in Chile, one at the South Pole, and again, no definite lower limit there. Dark matter, again, the problem is we have this incredible parameter space, so many orders of magnitude in particle mass, okay, and in cross-section, and we've only filled in the tiniest part of this so far, in sort of roughly the WIMP region, a little bit in the Axion region. But these are the regions that we probe, and most of this space is unprobable at the moment. And if it's only gravitational interaction, it's completely hopeless. And so here are the experiments that are underway, underground direct detection and indirect detection. This one is actually the only, I think, possible detection to date. And this is a hugely significant gamma ray excess in the center of our galaxy where there is lots of dark matter. The problem is this was actually predicted before the Fermi satellite flew. There should be an excess there from dark matter relations. But since then, there was a new theory that emerged, the theory of old recycled millisecond pulsars, which there are many, and which are known to be gamma ray sources. So there are 2 theories that probably could equally well explain the current data. And so I would say dark matter's got a 50% chance of being right, which would be wonderful, but we're not there yet, and that will take new experiments. And then finally, we're actively discussing some incredible, here's the LHC, some incredible future collider, which may or may not find evidence for cosmological problems. It's unlikely, but the particle people are very optimistic. Finally, maybe gravity is completely wrong, and we modify that. And again, the problem there is there are many papers on this stuff, but there's a huge parameter space to cover in terms of size and mass, and no indications whatsoever to date that Einstein got it wrong. So I think, it's a weird time. So in common, for all these experiments, you have to ask, well, they're going for precision, but there's no guaranteed breakthrough, and the budgets proposed for the next generation are mind-boggling. So at some point, you can't do them all. At some point, you have to make a choice. So I would say we need a compelling return for these very expensive science projects. In half a century, we've gone from 50% to 1% precision in the CMB. That's remarkable. The next generation of galaxy surveys will get us down to 0.1% precision from the 1% of the microwave. That's incredible too. But I think we need to aim higher, and we need accuracy as well as precision. So let me give you 2 examples in my remaining couple of minutes. Oh, sorry. So one is the spectral distortions of the microwave background. Now, the microwave background was measured to be a black body by the Kobe experiment in 1990, okay? Now, it should not be a perfect black body, but it is. And that means that at some level you must find distortions, otherwise you can't believe a word they tell us about the early universe, right? Because there's all sorts of structure that added to the microwave background. And much of it is, some of it's called the so-called mu distortion effect. I don't have time to go into that, but basically, here is what we measure these are 400 sigma error bars on the black body spectrum. This is what we expect to be finding from heating in the early universe, basically generation of high energy photons from depletion of lower energy photons, etc. All this sort of thing is predicted by theory. Just Bremsstrahlung, simple stuff. So if you can do this with all of these dwarf galaxy precursors, they were baryons, they're in the early universe, and they basically had friction with the microwave background. They must indicate some heat transfer. Has to be there. It's predicted by theory. They should generate this mu distortion. Just as the larger fluctuations gave you radiation damping that led to the wiggles in the spectrum, the small ones should, you can't see them directly, but only indirectly through their effect on the spectrum. And so the idea is that we'll be able to basically, what we can now do on microwave background logical structure, we can go to smaller scales, and if we can ever measure this predicted mu distortion, we'll know if there really is stuff there on, it's a prediction of our standard model. There should be small seeds, small galaxies, but we know they're formed, they must have had seeds, and they should lead to this prediction. So that's one thing to do. And the problem, of course, is that we've had projects, it's a very expensive project. One was rejected twice by NASA. The current hope is this. ESA, in its projection for the so-called Voyage 2050 program, is predicting that we should, one of its major goals, one is gravity waves, another one is microwave background distortions. It's an L-class mission with a 1 meter scale telescope and a Fourier transform spectrometer. That's in the current planning. This number, 10 to the minus 4, is where we are now, hopeless for doing cosmology. It's telling you CMB is great, but you have to improve this by 4 orders of magnitude. We can do that, or 5. It's not impossible. The amazing thing you can do is when we improve that, is you can measure the recombination of the early universe. To me, this is the holy grail of cosmology. Hydrogen and helium recombination lines. This is their signal in the cosmic microwave background. That would be amazing, but unfortunately the next slot that's open in ESA for this is 2065. So be patient. It's for the young generation, literally here. And then lunar radio telescopes. So this is for the not quite so young generation, because this is happening now. And let me just end with this, really. 21 centimeter emission. We want to probe redshift 50, roughly, to see the dark ages. That means 21 centimeter is now 10 meter wavelength, right? And with this, you can achieve many times the CMB resolution with an array of dipoles on the moon, basically, that may have to spread over many kilometers, okay? And you might need millions of them, but all of that is feasible now. And why go to the moon? Why go to the far side? Well, there's no ionosphere. On the Earth, you can't do this at all. There's no terrestrial radio interference on the far side. And it's the most radio quiet environment in the entire inner solar system. If you want to get to this is what you have to do. You have this huge background from our galaxy mostly and others around us. So you're looking for millikelvin signals in 1,000 Kelvin foreground, which is difficult, that's for sure. And this is what you're ultimately looking for. So you're trying to measure. Here we have the microwave background or scattering service. Here we have the galaxy surveys, measuring correlations, non-Gaussian correlations ultimately. But early in the universe, there were amazing things predicted just after inflation. And these are the things that we have not measured yet on the microwave background sky. We never will, but we can do this in the dark ages. And there's a reason for that. And that is because we have so much power. Basically, the galaxies on the sky, they're precursors, they're limited by radiation damping. 21 series not. We can directly see the 21 signal. So we have, 1 million building blocks per galaxy. That gives you, not just millions of pixels on the sky, but trillions. And that increases the incredible power of what you can do. Okay, so the far side of the moon is the key to doing this. Excuse me. So the first step is the monopole. This is what we did for the CMB. And this is what we are planning next year in January. Is the first experiment to go onto the far side. Actually, it follows the Chinese one earlier that did not work, but for various reasons. But this one will basically has a tripole actually, and we'll look for this dark ages signal. Not much hope of finding it. It's a trial experiment, but it's that you have to determine all the environmental issues, etc. But that's the ultimate aim of the experiment. And then I put Zuli's name there, but this is the DSL Lunar Orbit Array projected for 1 year later, 2028. There'll be an interferometer of 8 satellites going around the moon and basically trying to, with simple dipoles, and trying to get maps of the dark ages. So that's the immediate future. And there's a similar Indian experiment called Pratyush with maybe a slightly longer time scale to do something similar, orbit around the moon. Okay, so why are we doing this? So the ultimate goal of the fluctuations, 21 centimeter, it's to measure a prediction of inflation, which is called primordial non-Gaussianity. And that's a fundamental prediction. It's even more fundamental than the tensor to scalar mode prediction because we know this has to be there and at some measurable level, okay? And that is because there are predictions of what this level should be, basically from theoretical papers over the years, and in terms of a correction parameter delta t over t, it's 0.01 is what you're looking for. To get this, unfortunately, you need huge arrays of dipoles. So this is the story, unfortunately. With the microwave background, we have limits of order 10 on this magic parameter. With the new surveys, we can improve that of galaxies down to order 1, and we have basically 100 million galaxies that are usable in these surveys, so that gives you improved accuracy. But finally, with the dark ages, if we get this right, eventually, we have so much power, we can get all the way down to this 0.01 level, which is the magic value, but you need huge arrays of dipoles. Okay, so what are we going to do about this experimentally? So first, this is the European. These are imprinted dipoles on basically inflated tubes. That's one idea. This is another idea from Zuli Chen, a Chinese project, to have imprinted dipoles on meshes spread over the moon. And he showed us various ways of the architecture for this, etc. And possibly leading to experiments that will be as powerful enough to look for these signals. Okay. So I would say that's a promising proof of inflation. Very good. So I think I have to finish up here. And so perspectives for the future, I think we're looking at microwave background, spectral distortions is a major thing, low frequency radio arrays. What I didn't tell you about was the moon is a great place to do optical interferometry. There's no atmosphere on the moon. It's a nice stable surface. Stars don't twinkle. So it's a great place to search for exoplanets. You know, on the Earth, we did this with the VLT. We got a Nobel Prize for detecting the black hole at the center of the galaxy, but it did interferometry with basically milliarc-second integration times, the twinkling of the stars. On the moon, you can integrate for minutes, for hours even, you know. It makes a hell of a difference. What you do with an 8-meter telescope on the Earth, you can do with a 5-centimeter telescope on the moon in terms of sensitivity. It's totally amazing future. Not been explored yet at all, but it's going to happen on the moon. I have no doubt about that. And then along the way, we'll get there, I think, tensions, paradigm shift system, or whatever. And it's going to be, because these time scales are basically so long that I think for the moon, we're talking about 10 to 15 years, you know, so 2065. And for the flagship space missions, which is pretty bad. But for space, now is the time, actually. And we can expect to have many of these things on surface on the moon, 2040 plus, which is a reasonable time scale if you've recently got your PhD, right? So it's a great project to be in, actually. Okay, so I think we're making great progress. I would say there are no gold standard violations yet in our standard model, and we have no idea where else to go. So we should stick with that for the moment. So thank you.
Thank you so much for a fantastic present. So we can either have a bit of a discussion now, you know, amongst ourselves in this room, or we can go out in the front and have more discussions there. I don't know how everyone feels about.
See if there's any questions for Joe first.
Yeah, we'll get some questions first for Joe.
Can I ask one then, please? What's your thinking, Joe, on if we throw away the cosmological principle?
Well, you know, I showed this slide of the newest DESI results. When I stare at that, I see no reason to throw it away. Let me stop there. I mean, maybe in the more local universe, people are worrying a lot, but when you look far away, it looks, you know, pretty isotropic to me.
The definition of far away has changed over the last 40
Sure.
years.
Yeah, but okay. Yes, Marco.
I ask a kind of related question. There is, so the standard model is flat lambda CDM. So two questions. One on the flat. A few years ago, you promoted the idea that perhaps there is some curvature. What's your current thinking on that, about curvature?
Yes.
And the second part is, what really makes lambda CDM as a model? What are the main components? Which one can be maybe in the future change and still we can still call it lambda CDM? In particular, I refer to the fact that maybe the talk from Francesco. What is that really incompatible with lambda CDM to have a very, very, very large structure, or can we still retain that type of very, very large structure and still call it lambda CDM?
Well, I would say if the large structures are subdominant, then you know that's fine for lambda CDM. If you want the universe to be Bianchi 1 or something, which is probably the only model that might just work, then it's different. But there's just no evidence for anything else at this point. If we had an alternative model, that would be great, but I haven't seen one, and that's part of the problem.
And on the curvature?
On the curvature, I think there's no evidence for it at this point in time, but you know, again, people debate that. But that's a great thing to try to measure, of course. I totally agree. Yes.
Thank you. So you said the talk with in a philosophical note, and I want to get back to it. There's this very interesting chapter in the book, The Philosophy of Astronomy, written by, I don't know how it's pronounced, Marie Lugan, something like that. And in it, she summarizes all the efforts towards measuring the Hubble constant. And she argues that she doesn't believe that it constitutes a crisis because it's an issue of temporary discrepancy versus residual versus an actual frequency. And we need to get better measurements of the different or systematics to get to know systematics. To know whether that's the origin of the discrepancy or if it's a real one. So and you conclude that there's no, that you don't think this is a problem, we don't have to worry about it that much, as in we're not, the field's not dying, as in we might need new physics. So what's your point, what's your point of view, what do you think about it? Do you think there will ever be a time where the precision we achieve in our instruments is good enough so that we will know if this is residual discrepancy or not?
Well, look, I think it, depends which particular anomaly or crisis you're referring to. Sticking to the Hubble constant, I think the big issue now is data systematics for me and many people. I would guess half the community is worried about that. The other half blindly goes along with Adam Rees. But so when you have that much of resistance, it's clear there is something more to be done. And there surely are new studies on the horizon which are doing just this. We have to wait a year or two to get, many more supernovae with more control over their environments, et cetera, et cetera. So I think there are real issues there. And the same is true probably for time variation of dark energy, which is a far weaker thing. But yeah, so I just, I'm not worried by crisis. The fact that we can get along perfectly well with the current model until we come to a real, crucial blockage, and I don't think we've got there yet. Yeah. Yeah.
Just a question and a comment about what you said about Adam Rees. So a lot of my naive knowledge of Adam Rees' work from a book by Dr. Harry Keffin, he's a CERN physicist, and he was summarising that within the astrophysics community, discussions of the Hubble tension, or the Hubble constant coming from the distance ladder, the new research that involves the asymptotic red giant branch does change some of the general consensus on that. Do you think that will be enough to kind of meet in the middle with what the cosmologists are doing, like you said, with alleviating the Hubble tension, but not completely solving it? Do you think the astrophysics side of it will have enough of an impact to resolve it?
Yeah, all of that is very important, right? So the tip of the red giant approach led by Wendy Friedman is great. It gives you a different value, it seems, and both they and the supernova community are demanding new data, new observations to tighten their results. To me, maybe the most interesting option is the one that's being led by Sherry Sue and others, which is looking for the next Refstal event, which is predicted to happen in a year or two. And in that time delay, the multiple image of a supernova gives you an incredible example of measuring the Hubble from the time delay on the site. And that event and more of those, to me, I like that. They're geometric. They don't depend on all these horrible data systematics. That's very attractive about that.
Thank you. I think that's probably a good point to stop now. The outside room is, still open for people to hang around and continue some discussions and etc. And I'd just like to thank you all for coming to this conference and making it wonderful. I hope you've all enjoyed it as much as I have. And I hope to see you at the next one. I'm not hosting next year.
Just before you all go, there's one person we haven't thanked yet, without whom this week just would not have happened. She's done a fantastic job organising this week. Many, many of you have said to me, what a well-organised conference. I said, I can't take any of the credit for that whatsoever. It's all down to Alexia. So let's just thank Alexia. Thank you all for coming. We wish you a safe journey home.